Very good morning and welcome to everyone here on the live YouTube channel of the IUCAA SciPop. I am Samir Dhurde and it is a pleasure to have you here and watching our National Science Day programs virtually with us and celebrating this very important day for all scientists and science-minded people in the country. India celebrates its National Science Day every year on 28th February, and IUCAA also celebrates it with a lot of fervor, and a lot of interest is shown by all the people, and we have thousands of people visiting us. This has been a particularly difficult year for everyone, including people who do science. But our initiative to share all the science and the astronomy, astrophysics that we do here has not reduced at all. And the work that has been continuing will still be brought to you today in form of various short talks and poster demonstrations and a lot of interactive elements which are there in our program. So this is something we have lined up for you today. Now, to begin the day, let us, we'll have a short round of understanding what is IUCAA Science Day, what is the National Science Day, what is science all about. Yeah. And then we'll go into the talk sessions at 10 a.m. I will now actually move on to a message from our director, Professor Shomak Raichaudhary, introducing you to and welcoming you to the IUCAA Science Day celebrations.
30 years, we have been holding every year, of course, as part of our National Science Day celebrations for the last 30 years, we have been holding very extensive exhibition and an open house for everybody, for school children and for the general public to come and visit IUCAA. And over the last few years, we've had 10,000 to 15,000 people visit us on the Science Day. This year, we are very sorry to say that we cannot do this because of the pandemic. And what we have done is we have tried our best to take our celebrations online so that a larger number of people also can take part in our celebrations. We now can reach the entire world, we can reach the entire nation, as we can reach everybody around us. And this will be broadcast on IUCAA SciPop's YouTube channel. And so please follow us around the Science Day. And the detailed program is out. And please look at it and come and join us for the celebration of science.
So with that message from our director, Professor Shomak Raichaudhary, we will now go on to celebrating this day with all of you present here. And I can check the YouTube channel now. We have around 120 people watching now. So again, a very warm welcome. And of course, from our director, Professor Shomak Raichaudhary. Sorry, this needs to be now. Okay, so we also have my co-host Sonal Thorve joining us again from the IUCAA Science Center, and we are here in this lovely place where we do a lot of science activities throughout the year. As Professor has just said, we get thousands of people on Science Day, but then throughout the year at the IUCAA Muktangan Vidyan Shodhika, we keep celebrating science. And we keep doing live in-person events for everybody, including school students, teachers, amateur astronomers, and anybody who is interested in this very exciting subject called astronomy. Okay, it's the study of the sky, and we celebrate it, and we share this particular, this is the speciality of IUCAA, that we use telescopes of various kinds to look at objects in the sky and find out the wonders and the mysteries of the universe. A lot of answers are being found out, and we'll be sharing them with you today through this medium. Welcome Sonal, and आप कुछ हमें हमारे हिंदी भाषी लोग इसके कुछ बता सकते हैं।
यस, थैंक यू समीर। सो हम जैसा हमारे डायरेक्टर सर ने मैसेज दिया था कि आयुका में हर साल बहुत बड़े पैमाने पे ये जो राष्ट्रीय विज्ञान दिवस है ये मनाया जाता है। 10,000 कम से कम लोग आयुका हर साल विजिट करते हैं। सो सिर्फ नेशनल साइंस डे ही नहीं, पूरे साल भर आयुका के मुक्तांगन विज्ञान शोधिका जो है वहाँ पे पब्लिक के लिए, बच्चों के लिए हमेशा कुछ ना कुछ तो होता ही रहता है। सो ये प्लेस जो है, ये जगह जो है, ये हैपनिंग है, यहाँ पे हमेशा कुछ ना कुछ होता रहता है। तो मुझे लगता है कि हमें इसकी झलक भी हम अब देखने जा रहे हैं। सो समीर, क्या हम ये झलक देख सकते हैं?
जरूर जरूर। तो हर साल जैसे हम साइंस डे मनाते हैं, आई थिंक हमें बहुत सारे ईमेल्स आ रहे थे, वी वर गेटिंग सो मेनी ईमेल्स एंड मैसेजेस सेइंग जस्ट लेट अस इनटू द कैंपस एंड लेट अस हैव अ लुक एंड एंजॉय द प्रोग्राम्स लाइक वी डू एवरी ईयर। बट देन अगेन दिस इज अ डिफिकल्ट ईयर, वी हैव टू ऑल कीप रिस्ट्रेंट्स। हमें कोशिश करनी पड़ेगी कि कोरोना को हम बीट कर सके। साइंस हमेशा कोशिश कर रहे हैं, हम हमारे सारे साइंटिस्ट लगे हुए हैं कि इसको हम रोक सके, लेकिन अभी तक ये रुका नहीं है और हमें कोशिश करनी पड़ेगी कि हम सोशल डिस्टेंसिंग रखें और थोड़ा संयम बरतें। तो we'll be patient, but then we don't want you to lose out on that feeling. So we start right away by showing you a few clips from our previous science day, so you get a feel of kind of walking around the campus. So have a look.
Such a great crowd. I'm so happy.
बाकी सर्वजण शांत काय होईल. Okay, so that was such a nostalgic journey through the campus of IUCAA, and we had fun looking at all the people visiting us. Now, this is something we are really missing, but hopefully the lineup of various things will make up for it. We have next a quick look at what is science and what is scientific temper by one of our professors here. Just have a look and then we'll come back to you with the details of the program today.
Hello, my name is Dibarati Chatterjee. I am an associate professor at the Inter-University Center for Astronomy and Astrophysics in Pune. Welcome to IUCAA. What are we discussing today? We are talking about what is science. So what do you think is science? The word science comes from the Latin word scientia, which means to know. So what is it that we want to know? Practically everything around us. How are things happening when they are happening? Why do things work? When we look up to the sky, we see the stars, the sun, the planets moving. We ask ourselves, where did we come from? Where are we going? Science helps us decode the secrets of the universe. So science is nothing but the art of acquiring and sharing knowledge in a systematic way. So what do I mean by a systematic way? I mean by asking questions and trying to answer them in a logical and consistent way. So why do we do science at all? It's because by analyzing our past and our present, science gives us the power to predict the future. Let's take an example. Newton, Einstein, Galileo, they put forward the theory of gravity. So the theory of gravity not only helps us to understand the motion of cosmic objects in the universe, but it also helps us navigate our cars with the help of GPS on our phones. From historical times, we have been passing down knowledge from generation to generation. Nowadays, science is carried out in research institutes like IUCAA, at universities, in laboratories. But is science only restricted to laboratories? Science is all around us. So let us question the things around us, try to find the answers with the help of science. Stay curious, and most of all, keep calm and do science.
Good roundup of what is science. Now we can go on to quickly having a look at the day's programs. And of course, the introductions and the beginning of the celebrations has just started here with our scientists here, the astronomers here presenting to you what they feel about science and the science day itself. Okay, we'll have one more short video after this. But then the celebrations, the events of the celebrations start at 10 o'clock with several short talks. The schedule is such that we'll have a talk at every 40 minutes or so, and starting at 10 a.m. with primordial black holes, which is black holes are a very popular subject. So Swagat Mishra will be telling us about that. Variability in the sky and what does it tell us will be presented by Yash Bhargav at 10:40 a.m. 11:20 a.m. we'll have Professor Shubhodip Deb, telling us about how our journey went from sundials to atomic clocks, which are finding a very important use in science. Then at 12, we have Professor Neeraj Gupta presenting science and the Square Kilometer Array, which is a very large telescope, radio telescope coming up in the world, the largest in that. Then at 12:40, we'll have Professor Ram Prakash presenting to us the 30-meter telescope project. So both of these projects, IUCAA is a partner in, and we are very eager to see them come up and produce great results in astronomy, astrophysics. We have after that a few other programs, very different programs other than talks. So we will have a special walkthrough. Now, IUCAA Giravali Observatory is a place where IUCAA's own telescope, a 2-meter class telescope is there. And so we'll have a virtual visit to it. I'm sure you people will be very interested in having a look at what is inside a real observatory, which is used by astronomers, a real grand scale observatory, not just small telescopes like you see in the movies. So this will be a walkthrough to a telescope which is much taller than a human being. And so stay tuned for that. Of course, in between we'll have also a lot of short events where we will have some short films about good images of the sky, etc. Then 2 o'clock, again, a very popular event from IUCAA Science Day, Ask a Scientist event, in which we have very popular and very well-known Professor Jayant Vishnu Narlikar answering questions live. Okay, along with him will be Dr. Mangala Narlikar, his wife, and he's also a mathematician and a scientist. We have Professor Shomak Rai Chaudhary, who's the director of IUCAA, and there will be Professor Surud More and Dr. Anuprita More, who will be coordinating the program. So these 5 scientists will be available for you to live ask questions live. In case you have already sent your questions through our bit.ly link, which was announced earlier, then we'll be taking them, of course. But stay tuned, because we will go on for almost 1.5 hours. So there will be a chance for you to ask questions directly through our YouTube live chat box. So put your suggestions in the chat box, maybe here or here. I'm not sure where it is for you. So do that. And then after that, we'll have some special sessions in which we have to, of course, tell you about the research posters, which every year are shown at IUCAA. We have a big exhibition of posters in which, as you saw in the videos, a lot of researchers at IUCAA, they stand there throughout the day, explain the posters to everyone. We are not able to do this year, but there is a website, and we'll just send you the link through the chat, or we'll also display it here, flash it here. So you can visit that website and have a look at all the research posters. And if you have any questions, you can put in your questions just near that research poster. Okay, and you will be able to get answers to those questions. Some of those questions we'll try to answer during this period after 3:30. There'll also be something about the shared science drive that IUCAA has been taking up, and that will lead on to another highlight program of the evening, which is the public lectures. So every year we present to you lectures which are very simple and possible to understand for everyone, and our practicing scientists, practicing astronomers and astrophysicists present the work which deserved the Nobel Prize of the previous year. Okay, so they present you this work in very simple ways. So we have today, 2 great speakers, Professor Subhadip Sarkar from IIT Gandhinagar and Professor Dipankar Bhattacharya from IUCAA. They will be presenting to you this Nobel Prize about black holes. So of course, everybody has come for black holes and more information about that. So do stay tuned at 5:30 ahead for these 2 very interesting talks. So that's a roundup of the basic program, but IUCAA programs are other than that are also going on, and we'll probably have some follow-up things throughout the next week. So keep a lookout for that. It will be announced on our YouTube channel through a premiere as well. So Sonal, आप इसको थोड़ा सबको समझ में आए, इसलिए आप थोड़ा हिंदी में भी बता दीजिए. सोनल, आपका माइक म्यूट है.
जैसे कि आप सबने सुना, एक बहुत ही इंटरेस्टिंग सा लाइनअप है आज प्रोग्राम्स का. हम कोशिश कर रहे हैं कि ज़्यादा से ज़्यादा विज्ञान आप तक पहुँचे. तो इसमें सबसे पहले तो 10 बजे शुरुआत होगी हमारे संक्षिप्त वार्ताओं से, जिसमें बहुत ही इंटरेस्टिंग, जैसे ब्लैक होल्स है, आकाश में परिवर्तनशीलता है, या फिर धूप घड़ी से लेके, जिसे हम सौर घड़ी भी बोलते हैं, उससे लेके एटॉमिक क्लॉक तक हमारी जर्नी कैसे हुई, और 30 मीटर दूरबीन या स्क्वायर किलोमीटर अरे, इन जैसी अपकमिंग जो मेगा प्रोजेक्ट्स हैं, इनके बारे में हम आज सुनने जा रहे हैं. ये जो टॉक्स होंगे ये संक्षिप्त होंगे और ये 10 बजे से लेके 1 बजे तक चलेंगे. और हम यहाँ तक रुकने वाले नहीं हैं। इसके बाद हम बहुत ही इंटरेस्टिंग से कुछ नए वीडियोस भी देखने वाले हैं, जैसे आयुका गिरावली ऑब्जर्वेटरी, जो आयुका की दूरबीन है, तो वो देखने का बहुत लोगों का मन होता है। तो इस साल हम लेकर आए हैं एक नई वीडियो जिसमें आप आयुका गिरावली ऑब्जर्वेटरी की वर्चुअल टूर कर सकते हैं। उसके बाद 2 बजे हमारा एक बहुत ही अहम सेशन रहता है, जिसमें प्रोफेसर शोमक राय चौधरी, जो आयुका के डायरेक्टर हैं, प्रोफेसर जयंत नार्लिकर जी और मंगलाताई नार्लिकर, तो ये जो है हमारे साथ क्वेश्चन आंसर सेशन, मतलब सवाल जवाब का एक सेशन है, इनमें जुड़ने वाले हैं। और ये सेशन जो है, इनमें हमारा साथ देंगे प्रोफेसर सुरुद मोरे एंड डॉक्टर अनुप्रीता मोरे। इसके बाद भी कई विशेष सत्र है, जैसे आयुका ने इस साल एक नया अभियान शुरू किया है जिसका नाम है आयुका शेयर साइंस ड्राइव, जिसमें इंडियन रीजनल लैंग्वेजेस, मतलब भारतीय क्षेत्रीय भाषाओं में हम विज्ञान लोगों के साथ साझा करना चाहते हैं। तो इसके बारे में एक छोटी सी हम फिल्म देखेंगे, और उसके साथ उसके बाद शाम को हमारे नोबेल प्राइज टॉक्स जो है, जो हमारे नेशनल साइंस डे की स्पेशलिटी रहती है, 2020 में जो नोबेल प्राइज मिले हैं, तो उनके बारे में हमें बताने जा रहे हैं प्रोफेसर सुदीप्तो सरकार एंड प्रोफेसर दीपांकर भट्टाचार्य। तो हमारे साथ बने रहिएगा आयुका साइपॉप के चैनल पे। धन्यवाद।
Great. So now we come to a quick video about what is the event that we are celebrating through the National Science Day. Many of you, of course, know that it is the discovery of the Raman effect by Professor C.V. Raman, who was the first science Nobel Prize winner for India. But let's have a little detailed understanding of what is National Science Day celebrating from our Professor Somak Rai Chaudhary, our director.
Hello, my name.
Every year we celebrate the National Science Day in India at the end of February to commemorate a very special landmark in the history of Indian science. A lot has happened in Indian science over the ages, but in the 20th century, one of the most important events that happened was the discovery of the Raman effect by C.V. Raman in Calcutta, at the Indian Association for Cultivation of Science. It was a very important event for many reasons. One is, C.V. Raman himself was not a scientist by profession for a long period of his life. He was an accountant, and he pursued physics as an interest. And an Indian institution of science was so liberal at that time in the 1910s and 1920s that they gave him the chance of performing his wonderful ideas for experiments in the evening after work in their laboratories. I think current laboratories have a lot to learn from this kind of an approach. During these experiments, C.V. Raman discovered the Raman effect, characterized it, explained it, and also went on to do some very important pieces of work. This Science Day itself commemorates the day on which the Raman effect paper was accepted for publication. And this led to a new confidence in Indian science, because that led to a Nobel Prize in physics, the first to be won by an Indian working in India. As I said, this event itself has many, many different connotations which serve as a lesson for us in contemporary India, where we are learning to be self-reliant. We are trying to lead the world in many scientific endeavors, and we are also trying to show the general public and the young people studying in India that science is a wonderful place to go in their careers, and it is possible to study in India, to do research in India, and still lead the world. C.V. Raman was an accountant general, part of the accountancy service of the Indian government. He managed to do world-breaking science by sheer hard work, working in his spare time. This gives the message that science is possible with hard work, science is possible against all adversity, and science needs to be one of the major things that everybody, all people, not just scientists working in labs, need to work on, need to know about, and science has to reach everybody. So National Science Day has this mandate. It brings the science.
Perfect.
National Science Day has this mandate. It brings the science out of the research laboratories and the universities to the common person.
He flashed her, huh? Website flashed her.
It talks about, it shows how science is done, it shows how Indian science is done, and it inspires Indian scientists to talk to the general public, to school students, to school teachers, and tell them about the current advances that are happening in science. It talks about how science is done in the whole world, and it talks about how Indians have done science in history. In IUCAA, we picked up this theme in the early 1990s, in the early years of IUCAA, and for about 30 years or so, we have been celebrating National Science Day in order to take our science out to the public, in order to show young people how a career in science is possible, how science improves our lives in every way. When we started doing this, not many research laboratories or universities did this. National Science Day used to be celebrated by the government, but not by many scientists. I'm very happy to say that after this path-breaking work that IUCAA had done in the 1990s, nowadays a lot of scientific institutions take part in Science Day activities, and we see that on Science Day, the general public has also got into get into festive mode on National Science Day like any other festival, and they go and visit scientific institutions because they know that they will be welcome there. This is the message.
So with that lovely introduction to what is the Science Day and a very in-depth information about it, we begin today's series of events that we have lined up for you. Now to come to the first short talk about black holes. Yes, but these are very different black holes, which you'll hear from our speaker, Dr. Swagat Misra, who's going to come here very soon and join us here in the meeting room. Swagat is a researcher at IUCAA, and all the people here who are giving talks are doing research in astrophysics in IUCAA, and they have taken out time to make things that way they research very easy for you. So let us have Dr. Swagat Mishra here speaking to us about primordial black holes right from the Big Bang. Welcome, Swagat. Good morning.
Hello. Hi, Samir. Good morning. Thank you.
Yeah. So you have the floor, and you can go on, and we'll have a question answer session at the end. So just putting in this bit that people can type in their questions in the YouTube live chat so that we can read them out to the speaker.
Sure.
Thank you for being here, Swagat.
Hello, everyone. I think my my screen should be full screen now and visible.
It's perfect. Yep. Yes.
So today I'm going to talk about primordial black holes. I would usually on Science Day talk about cosmology, but since all of our previous talks are recorded on YouTube, So I thought to talk about a little different topic, which is primordial black holes, especially because black holes have really become the most debated and the most talked about topics over the past few years. And we're also going to hear the last year's Physics Nobel Prize, which was awarded to for many aspects of black holes. We're going to hear lectures about it in the evening today. But I'm going to talk about a particular types of black holes, which are primordial black holes. However, before we jump into the topic of primordial black holes, I'd like to give you a very short introduction to our universe, which would help us to understand these primordial black holes. If imagine that if we had a big eye, huge eye, then we can, and if we can see almost a big part of the universe where we have millions and millions of galaxies, okay, then the universe would probably look something like this. This is not a real photograph; it's a computer simulation, but it will kind of look like this, where each bright dot in this diagram is like a galaxy, and then what you see is like there is a web-like structure. There are places where it's quite bright, and then there are some void kind of structure. So this is how our universe looks on very large scales. And if you zoom into a very tiny portion of it, then our universe is going to look like this. This should seem more familiar, where all these objects are galaxies. So we see within a small angle in the sky, we see thousands of galaxies. That's our universe today. But we also know that our universe is expanding. So all these galaxies, they are going away from each other. But this picture of universe, the way it looks today, is not always the same. Our universe is evolving with time. And in the past, our universe looked very, very different from how it looks today. So here is the short history of our universe. Today, we see our universe having all these clusters of galaxies. Okay? And then inside the galaxies, there are stars, there are black holes also, then there are planets and stuff. But if you go back a long time back, then you would see that there was a time when universe didn't have these stars and galaxies, but it was filled with hydrogen and helium gas mostly. Okay. But if you go even further in time, up to the point, so today our universe is roughly about 14 billion years old. So 13.8 billion years old. Okay. But if you go back to a time when our universe is roughly around 4 lakh years old, by that time, our universe was so hot that it was in a state of a plasma. And it was dense and hot and plasma state, where the nucleus of atoms and electrons were separated and moving around like a plasma. I'm going to talk about this plasma phase in a minute, but that plasma was expanding, and expanding plasma or expanding gas cools down, and then after it cooled down, it formed neutral atoms, okay, around the time when it was 4 lakh years old. And then slowly over the long period of time, all this neutral atom gas, they got slowly collapsed under gravity to form stars and galaxies. Okay, because initially this gas distribution was not completely uniform. Okay? There are places where you have a little higher density, and then places where little lower densities. And these higher densities would collapse under gravity over billions of years, and then form the structure, the familiar photo of the universe that I showed you. Now, our universe has several components to it. There are the usual light or photons, electrons, protons and neutrons, as well as neutrinos. Also, there are dark matter and dark energy in the universe. Today, I'm not going to talk about dark matter and dark energy a lot, but know that this dark matter, which is there today, it has been there in the universe for the past 13.8 billion years. Okay, and it really helps to form structure in the universe. It makes universe clumpy, and so galaxies could form easily. Now, two time scales we have to remember a little bit. First thing is 1 second after the Big Bang. So 1 second after the Big Bang was the time somewhere here where the first nuclei started to form. Okay, so like helium nuclei would first start to form around 1 second. But if you go back a little ahead in time to this period, this diagram which you see here, this is about 4 lakh years after Big Bang, when the first atoms started to form. Okay. Now let me talk about the first early times. Okay, the hot dense plasma phase. In the plasma phase, earlier, there were all these electrons, protons, neutrinos, probably dark matter particles moving around. And slowly over the time, neutron and proton would combine, and then they will form the nucleus. Okay. This nucleus combination happened around 1 second. Before that, the very early universe was in a soup of quarks and electrons and neutrinos and photons and all sorts of particles. So this is a very crucial phase, very extremely hot. The temperature here would be much greater than 10 to the power 10 Kelvin. So 10 billion Kelvin. Okay, this is the hot universe which is there. Now, the general the conclusion that I want to tell you is that universe was initially a plasma state, and then it went on to neutral atoms and molecules, and over many millions of years, 4 stars formed, and then over billions of years, galaxies forms. Once you have the 4 stars, they could be really, really heavy, the 4 stars. And if they are really heavy, the core of the stars, after the star has burnt its fuel, its main sequence of its fuel, the core, if it is massive enough, it can collapse. If the core of a massive star collapses, then only black holes are formed. Okay, and this is the basic idea of black holes that we have. And in this talk, we're going to call these black holes, which are formed by big, huge stars whose cores collapse and to form black holes. We are going to call them as astrophysical black holes. And since they are formed from collapse of stars, their mass should be greater than mass of a star, or around mass of a star at least. So usually the mass of such astrophysical black holes would be at least around thrice of mass of our sun. Okay, I'm going to use mass of our sun quite a lot. I might call it once in a while m naught, but remember that this is mass of our sun, which is a typical star, and its mass is around 2 into 10 to the power 30 kg. So these are these astrophysical black holes. Now, so what are black holes? You're going to hear more about what are black holes from Professor Sudipta Sarkar's talk later. In a strict sense, black holes are regions of space-time which are so curved that nothing can escape from that region, and anything which goes into the region actually falls into it. To be particular, in Einstein's theory, a black hole has a lot of mass and energy and curvature right at its center. And then surrounding it, there is a sphere, which is called the Schwarzschild radius. This is a sphere of no return, in the sense that if let's say a particle is falling into the black hole, once it crosses this sphere, the particle cannot turn back and go out of it. This is according to Einstein's theory of relativity. Okay. So for us in this talk, we are going to think of a black hole as an object, a very heavy and very compact object, which is of the size of its Schwarzschild radius, okay, or horizon. We can also call it horizon. So we are going to think of black hole as some kind of a sphere, okay, a very compact sphere. And they are usually formed if you take a lot of matter and compress them into a very small volume. To be particular, you can take a lot of matter of mass m or mbh, take that amount of matter and compress it into a radius which is rbh. So if you compress such a large amount of matter into a small radius, then only you form a black hole. Okay. For our talk, this will be fine. Now, in principle, according to laws of physics, you should be able to make black holes of a range of possible masses. Especially, you can make black holes which are as light as 10 to the power minus 5 kg, which is really it's like a dust particle. Okay, and then you can make black holes which are as big as 10 billion solar mass. Okay, so 10 billion times heavier than our sun, or even more. You can also make it as heavy as the entire observable universe. But I'm putting this number because of some reason. So you can have 10 to the power 40 kg or 10 to the power minus 5 kg. These are the range of black holes. By the way, I remind you again that m naught is our solar mass of our sun. This is in principle, this should happen. However, let's see observationally whether black holes are hypothetical objects or we have observed them. Turns out we have observed them. We have given Nobel Prizes for this observation. So some of the important observations of black holes come from a combination of gravitational waves as well as X-ray. And these are usually binary black holes or one black hole and some other compact object or could be a star. So in particular, gravitational wave detectors have detected 50, around of the order of 50 binary black holes. So there are two black holes which were rotating around each other. As they rotate around each other, they lose energy by gravitational waves, little bit of energy. So they come closer and then lose even more, and finally they collapse. Finally they collide. And when the two black holes collide, they will give rise to a lot of gravitational waves, which we can detect. From there, we know that these black holes are there. And the typical masses of these black holes found in gravitational waves detection, as well as in X-ray observation of a black hole and another star rotating around it varies from around 3 solar mass to about 160 solar mass. So these are really heavy black holes we have detected. And then there are even heavier black holes that we have detected, which are called supermassive black holes. You are also going to hear about it in Professor Dipankar Bhattacharya's talk today. And they are found at the centers of galaxies, of different galaxies, as well as even heavier. So usually for a typical galaxy, like in our galaxy, there are these heavy black holes of million solar mass. And then there are AGNs, active galactic nuclei, where you have black holes which go up to several times, several billion solar mass. So all the way up to 10 billion solar mass black holes. These are the black holes that we have observed in nature by observation. So we know they exist for sure. However, we have never found a black hole whose mass is smaller than mass of a star. Okay, we have never found a black hole which is as heavy as a planet or as heavy as a mountain or asteroid. We have only found more heavier black holes. Okay, but if you can find a black hole which is smaller than mass of our sun, then such a discovery will be extremely exciting because of the following reason. But we are going to we'll call those black holes as primordial black holes rather than astrophysical black holes, because astrophysical black holes formed by collapse of stars, so they should have at least mass of our sun. They should be at least as heavy as 2 or 3 times mass of our sun. Okay, so we are now going to go into primordial black holes. Now, primordial black holes are black holes which formed not million years after the Big Bang because of collapse of stars, but early times in the universe, when universe was less than 1 second old. And I told you when our universe was less than 1 second old, it was a hot, dense plasma soup. So these primordial black holes are formed from this hot, dense plasma soup in the universe. Okay? So these are exciting objects. At that time, there was no stars. The entire universe was in a plasma state. Now, since they don't form by collapse of any star, they can have any mass in principle. I showed you the range of masses that is possible because by the laws of physics, and these black holes could have any mass. They could be extremely light as 10 to the power minus 5 gram, all the way up to billions of solar masses. Now, how do we know if we detect a black hole, whether it is a primordial black hole or not? Well, for sure, if you detect a black hole whose mass is smaller than mass of a sun, that's the proof of finding a primordial black hole. The question is, if they are formed in the hot, dense plasma state in the early universe, how are they formed? What forms these black holes? Well, the reason is the following, that our universe, when it was in a plasma state, it was roughly homogeneous and isotropic. So it looks uniform everywhere, but there were very small density fluctuations from point to point. That means that there were points where you have a little high density, and then there were points where you have a little low density. Okay. Now, these high densities, if you have high density, gravity will try to collapse it. But if there is a lot of light and photons and electrons are interacting with each other, light would try to push it out. So any kind of small fluctuations going to oscillate as long as universe is in a plasma state. Only later, when universe becomes neutral atoms, then these atoms come together slowly and then they form stars, millions of years after. But imagine that in the early universe, it is possible that at some point you have large density fluctuations. Like there's some point where density is very high. At those points, what would happen is that the pressure from light or photons cannot sustain this collapse. So the plasma in the universe locally will collapse to form a black hole. And these are these primordial black holes. So at different points, if you have high densities in the universe locally, then this will collapse to form black holes. And the mass of these black holes depend on when they are formed. The earlier they are formed, the heavier, the lighter is their mass. The later they are formed, the heavier is their mass. In particular, the mass of a black hole, which is formed about 1 second after the Big Bang, has about 6 into 10 to the power 5 solar mass. Okay, and things which are formed earlier would have even smaller mass. I give an example. The supermassive black hole, whose image we have sort of taken, the image around it in radio waves, has a mass of 6 billion solar mass. It has a radius of 10 to the power 10 kilometers, and it was formed, if it was a primordial black hole, it would be formed roughly around 3 hours after the Big Bang. But a solar mass black hole could be formed in the early universe, which would have a size of 3 kilometers, and it would have been formed around 10 to the power minus 6 seconds after Big Bang. You can also have Earth mass black hole, which is like 1 centimeter. It's a very tiny black hole. And this could have been formed 10 to the power minus 11 seconds after Big Bang. So you see these numbers. So if you detect any of these black holes in the universe, you are talking about physics or processes that happened that early in the universe. So these black holes, primordial black holes, are really a great tool to test very early universe physics. We know that around 4 seconds, the first nuclei formed, and so these black holes even before that, and they could be microscopic in size, as you saw. There's some black holes have micrometer, and so quantum mechanics becomes important. And thinking about quantum mechanics of these black holes, Stephen Hawking actually discovered the famous Hawking radiation. Let me talk for 1 minute on Hawking radiation. Now, Hawking radiation. So classically, there is this event horizon around the black hole, okay, a sphere, and it's a point of no return. So if something falls into it, cannot go out. But because of quantum mechanics, what happens is things leak out, things tunnel out of these black holes. And as particles and radiation tunnel out of these black holes, the black hole loses its mass and becomes smaller and smaller and lighter and lighter. The smaller it becomes, the even in an easier way it loses mass, because quantum mechanics becomes even important for even smaller black holes. And so the black hole keeps shrinking until it evaporates completely. This is called Hawking radiation. It's roughly a thermal or a black body radiation. And the temperature of Hawking radiation is inversely proportional to its mass. So smaller is the black hole, higher is the Hawking temperature. For a black hole which is as heavy as our mass of our sun, its Hawking temperature is incredibly small, 10 to the power minus 8 Kelvin, so we cannot detect it. But for a black hole which is smaller, like primordial black holes, like Earth mass, or even smaller, these black holes could have temperature all the way up to 1 degree or even higher. So these black holes we can detect, and then we can test Hawking radiation for sure. For a black hole which is about 10 to the power 15 gram, like a mountain mass, it will last all the way until the age of the universe, okay? Because it's evaporating. So if a black hole has a mass lighter than 10 to the power 15 gram, it will completely evaporate until today. So if it was born in the hot dense plasma during Big Bang, by today it will evaporate if it has a mass which is smaller than 10 to the power 15 gram. So you have an overall idea that these black holes are formed in the early universe, but once they form, they have several important cosmological implications as well as astrophysical implications. I do not have time to go through all of them today, but I'll just list them at least. That these black holes could be the dark matter in the universe. It's possible. Second thing, these black holes, primordial black holes, could really be these binary black holes from which we are detecting gravitational waves by LIGO, for example. And these primordial black holes, which are heavy, there could be heavy primordial black holes also. And if they're heavy, they could really be the origin of these supermassive black holes at the center of AGNs. Okay? And they can help us to probe the very early universe physics, as I told a little, because they're formed within a fraction of a second after Big Bang. And they can help us to test Hawking radiation, as well as they might have some significance for Planet 9. Now, Planet 9 is a hypothetical planet. It is proposed because of the following reason, that we see a lot of planets in our solar system beyond Neptune, whose orbits are kind of aligned because of some reason. Okay, so one of the way to explain it is that there is an object of mass around 5 to 10 times mass of Earth, which is making this behavior. Now, people have been searching for it by different methods, and they have not found it yet. So one of the possibilities that such a 5 to 10 Earth mass object could be a primordial black hole. So it's really a black hole possible that it's lurking out little outside Neptune, or maybe a little beyond Neptune, and it will have a size of roughly a few centimeters. Okay, so it's a very small black hole. And last year, a lot of people have discussed how, if it is a black hole, how to detect it, how to send probes and detect this black hole by a different method. So if you are interested, you should read about it. And if you're interested in Planet 9, Professor Surud More gave a talk at IUCAA 2 years back. You should have a look at this. This is my last slide on this talk. So the question is, I'm talking so much about primordial black holes. Have we observed them yet? The answer is no. We have never found a single primordial black holes as of now. But there are scopes of finding these primordial black holes. So what is plotted here is the mass of primordial black holes. And on the y-axis, if these primordial black holes are dark matter, what fraction of the total dark matter is composed by these primordial black holes? So there is some window here. The white parts here are allowed and the shaded parts are not allowed. So there are windows where you can have primordial black holes which can form all of dark matter in the universe. Okay, there are some interesting windows. Because of because primordial black holes give rise to Hawking radiation, very tiny black holes will give rise to gamma rays. And since you don't see some extra gamma rays in the universe, you know that many of them could not be there. So there are some constraints here. Then if a primordial black hole is passing through us and stars in, let's say, Andromeda galaxy, then they can cause by microlensing, by gravitational lensing, they can make the brightness of those stars increase momentarily. And observations made by scientists, including Professor Surud More at IUCAA, have put a large constant on these black holes, which can create a little increase in the amplitude brightness of stars overnight. Okay. So we have some interesting constants, but more constants will follow from gravitational wave observations as well as gravitational lensing like this in the near future. Okay. Now, what I didn't discuss in this topic in great detail is how these primordial black holes could be formed in the universe, the formation mechanism. But last year, I wrote an article in Mac Principle, which is meant for public in great details to understand in simpler language how these black holes could form. So if you like, you should have a look at least this article. This will give you a good idea about how the black holes are formed. Exactly how these large fluctuations of density can be created, which can collapse in the plasma. Okay, so I give you further references to read. The links here, you can anytime just type these links and get these articles. I also gave a public talk, a longer talk, 1 hour long talk last year on primordial black holes. You can have a look. And the link to the Planet 9 talk by Professor Surud More is also here. Before I end, I want to say that black holes for a long time was believed by classical physicists as extremely beautiful, stable spherical objects. But if you apply quantum mechanics, not so, and black holes would radiate. And by detecting these radiations, you can find what kind of black holes could be there, as well as you can test quantum mechanics and gravity together. I'll stop here. Thank you.
Thank you, Swagat. This was a lovely talk about something different. It's not about stars blowing up and becoming black holes. These are about original black holes right from the beginning. And so we'll take like 2-3 questions quickly before we go on to the next talk. Little time, but thanks for giving us this very simple look at your research. So one question is that can we apply black hole physics and thermodynamics, etc., to primordial black holes, because we don't know their, whether the physics applies at black hole, places. Sorry, Big Bang era. So this is from Yash Nilesh Soman.
The answer is yes. All the things that we know about big black holes can also be applied to primordial black holes. By the way, primordial black holes could also be big. I understand. I think that you are asking about these small primordial black holes. Yes, all of them can be applied, as long as the mass of these primordial black holes are greater than 10 to the power minus 5 kg. If they are smaller than this mass, then we need a full quantum theory of gravity. But otherwise, a mountain mass primordial black hole or a Earth mass primordial black hole, we are fine. And I just want to stress once, a Earth mass black hole whose mass is mass of Earth, would have a size of 1 centimeter, even smaller than 1 centimeter. Okay, so they're tiny objects. So quantum mechanics is important, but quantum gravity is not required for that.
Okay. We have several questions, but we'll take some relevant ones. Tanish Nandrebut wants to ask, or Tanish Nandre wants to ask, if a black hole with much higher mass slowly evaporates over the billions of years, can it become something like a primordial black hole?
No. If you start with a astrophysical black hole, let's say 10 times mass of our sun, and every black hole Hawking evaporates. So this black hole will Hawking evaporate. For this black hole to become much smaller than mass of our sun, it will take a long time. It will take trillions and trillions of years to become shrink and become smaller than mass of our sun. But still, we'll not call it primordial black holes. The reason is because if initially the black hole was formed by collapse of stars, then these are astrophysical black holes.
Okay.
Primordial black holes should be formed early in the universe.
Right. Okay. That's good to know. So we can't have a black hole formed close by and replicating a primordial black hole. All right. I'm just looking at one last question. So maybe this was not clear to people, that if primordial black holes have never been found or seen, then how were they discovered? Is the question.
But they have not been discovered. Very good question. See, they have not been discovered yet. These are theoretical predictions. Think of gravitational waves, for example. They were predicted in 1916, and they were first time experimentally detected in 2016. So it took 100 years to detect gravitational waves. Similarly, it can take a long time. But these are extremely interesting theoretical ideas, and they could really be there.
Lovely. So basically, I think astrophysicists are not just observational astronomers, but they combine observations with the theory as well, which is a lot of mathematics and physics combined, and the predictions can then be tested. So I think both are needed, and thank you for carrying on that research to lead us into into such deep mysteries of the early universe. Thank you very much, Swagat, for sharing this. We'll go on to the next talk, but thanks again for being here. Sonal, so who do we have next in this lineup? You're muted.
Yes, so we have Yash Bhargava next, who is going to talk about variability in the sky and what does it tell to us. So let us welcome Yash Bhargav, who is a research scholar at IUCAA. Welcome, Yash.
Yes.
Hi guys.
Good to have you here.
Yeah. So
you have the floor. Yes, please.
Wait for 10:40.
No, please. We can maybe we can have a quick chat about what you do here. We missed that with Swagat, unfortunately. But
yeah, sure, no problem.
How's your experience with IUCAA, etc.?
I'll be describing a bit about what I do in my talk.
Oh, you do? Okay. Right.
Yes. But still, I work on black hole X-ray binaries, and I'll describe it in a bit more detail, and I am happy to take any questions on it. So what I do is I try to understand the variability in these systems and what it does tell us about black holes in general, and what we can, if we can probe very close to the black hole. And what I study is the binaries which are in our own galaxy. So, yeah.
Okay.
And
right. So actually, I think we are a little ahead of time here. So that's why we are saying. So Swagat is still here. Swagat, could you still come on and अब थोड़ा सा हमारे दर्शकों को बता सकते हैं आपके IUCAA लाइफ के बारे में थोड़ा सा रिसर्चर लाइफ के बारे में. Thank you.
Sure. Yeah. So my IUCAA life is actually coming to an end very soon. I joined IUCAA in 2015. I did my PhD. I just completed my PhD in early January this year, and I had great time at IUCAA, both as a research scholar doing research in cosmology, as well as a science popularizer. I did a little bit of work with IUCAA SciPop. I gave a few talks, and I should say that National Science Day was one of my favorite events at IUCAA, probably the favorite event. And this year we are happy that we are doing it online, but we wish the pandemic was not there and we could do it offline. And it would have been great.
Great. और आपने आपका थोड़ा करियर प्रोग्रेशन कैसा है वो भी आप अगर बताएंगे तो, क्योंकि हमारे ऑडियंस में काफी स्टूडेंट्स हैं और करीब 350 लोग अभी देख रहे हैं आपको, तो आप थोड़ा सा बताइए आपका करियर प्रोग्रेशन कैसे रहा है एस्ट्रोफिजिक्स में.
मैंने मेरे हाई स्कूल के बाद आई डिड इंटीग्रेटेड मास्टर्स in physics from an institute called National Institute for Science Education and Research. This is in Bhubaneswar. It's called NISER usually. And there I studied quantum physics and particle physics as well as experimental physics. And then I spent about 1 year in an institute called CISA in Italy, where I studied mostly early universe cosmology. And then I came to IUCAA. I gave IUCAA entrance and I came to IUCAA. So you can come to IUCAA through this route by doing physics, masters in physics. You can also come from after doing BTech in engineering.
Okay, that's great. So all fields have a scope to come into astronomy. All they have to be interested in is in physics and mathematics. I think that's one of the important things to study. Lovely. Thank you for sharing this, Swagat. हम आई थिंक यश को भी यही सवाल पूछते हैं. यश आप वापस आ जाइए और प्लीज हमें बताइए कि आप कैसे IUCAA आए, कैसे आपकी.
सो मेरा जर्नी थोड़ा अलग था. सो आई डिड बैचलर्स एंड मास्टर डिग्रीज फ्रॉम IIT Bombay in energy engineering, and then I did a project with NTIFR on X-ray astronomy, and then I joined IUCAA and I gave the IUCAA entrance exam, and then I joined IUCAA in 2016.
Okay.
And this is my final year, so hope for the best.
Yes, all the best for that. Soon you'll be a Dr. Yash Bhargava. Lovely. So it's a good journey to have, and I think you're as you just said, we have around 350 people watching, so it's quite inspiring for them to come in here. So आपका जो research है, आपने जो black holes में research करने का कब सोचा, कैसे सोचा?
So first time I heard about black hole was in a stargazing session when I went to Wangani with a amateur astronomy group in Mumbai.
Okay.
So वहाँ पे they told they were showing Cygnus constellation, and they showed that there is Cygnus X1. And it was the first black hole to be discovered. I'm like, wow, this is interesting. And I was a 9th standard student, so I was very intrigued by it. And then I gave Olympiad exams, and that got me into astronomy. And then I joined the astronomy club in my college, and then I visited IUCAA as part of the Olympiad program, and this was very fascinating. So this pulled me over here.
Wonderful. That's actually a great tip to give to the students. There is a astronomy Olympiad which happens, and it's an international one. Indian students have been really winning laurels in it. So many gold medals, silver medals.
And I would encourage students to give that exam, and it starts off in 9th standard, where you require some basic physics to try to understand what is happening, and then you actually learn a lot of physics before you delve into higher educations as well. So that's a great place to be.
Wow. So yes, to all the students who are online, keep a lookout for this around 9th standard, 8th standard, if you're interested in astronomy, astrophysics. अगर आप चाहते हैं तो इंटरनेशनल एस्ट्रोनॉमी ओलंपियाड की टेस्ट का आप ध्यान रखिए. पहले तो आई थिंक इंडिया में आपको ट्रेनिंग दी जाएगी, और हमी बाबा सेंटर फॉर एजुकेशन इन मुंबई conducts that. So keep a lookout for that. That's another great route to get into astronomy, astrophysics, and be an expert in it. So thanks for sharing this, Yash. आपका टॉक आप I think हम शुरू कर सकते हैं.
Can I start with my talk?
Yes, please.
Okay, so I'll share my screen and let me know if everything is perfectly visible or not.
Sure.
Okay, can you see my screen?
Looking good and audible. Thank you.
Okay, great.
Okay, the floor is yours.
Yes. Great. Hi everyone. I'm Yash Bhargav, a PhD student at IUCAA, and today I'll give you a glimpse of what changes in the sky can tell us. So, being a scientist, we have to be inquisitive. So, let's question the premise of my talk itself. Is the night sky a constant? And ask, uh, if it is constant, then why do we care? And if it is not a constant, then what all changes in the sky? So, the answer is no, it is not a constant, and quite a lot of things change in the sky. So, what does that can tell us? Well, first thing is night sky is as a whole, it moves around during the night, which tells us that okay, well, the sky is changing, what we see is changing, but it's moving. So why do I care? But I wouldn't call it a variability. But there are things which do change across the night sky, and one of the statement which has stuck with me is that once you see a night sky, you will never see it again exactly the same. So do check out for that. So let's go from the most obvious changes to the most obscure changes. The first obvious change is the moon. It changes every night. So as you can see, it goes from a low phase to a high phase and then to a low phase again. So the low phase we call as new moon and the high phase we call as full moon. And the time it takes from moon to go from new to full to new is all defined as the typical length of the month. And month is has its origin in the name moon. The motion of the moon is also pretty interesting. As you know, that moon has a period of 28 days, and but it doesn't return to the exact same spot every time. That is something that is due to precession. So what happens is, if you have spun a top at some point in your life, you would have seen that the top spins like this at the end. And this is known as precession. What happens is your axis of rotation is also rotating. And due to this rotation, the moon orbits is also precessing. And therefore, the moon doesn't occupy the same spot in the sky every month. And this is also part of the reason you don't see the eclipse of the moon every full or new moon night. The other part of the reason being that the orbit is tilted and it goes out of the field of the sun and earth plane. So let's go to sun. Sun also moves in the sky. Well, across the day it does move, but across different days also it moves, and that is due to the inclination of the uh, axis of the Earth to the Sun Earth plane. So what happens is your Earth is tilted with by 23 degrees, and then at some points of the year it is pointed towards the sun, and at some points it is pointed away from the sun. So what happens is you get summer and during when it is pointed towards the sun, and winter when it is not pointed towards the sun. And due to this, your days are longer and shorter in summer and winter respectively. This motion has defined the calendar for us. What you see over here is a very nice composite which is made by taking the picture of the sun at the same spot on the same time of the day across the year. And you can see that it traces what is known as an analemma, which is a figure of 8. And so this shows us that sun indeed moves across the sky for during the year as well. So that's another kind of variability we see in the sky. Another motion, which is not that obvious, is planets. The word planet has a Greek origin and it means wanderers. The planets which we see with our naked eye is Mercury, Venus, Earth, Mars. Mercury, Venus, Mars, Jupiter, and Saturn. We do see Earth, but not in the sky. And interestingly, if you go out tonight, you'll see Mars, but if to see Jupiter and Saturn, you'll have to wake up very early tonight. And Mercury and Venus also show phases like the moon. So they change the shape as well. If you can think of a reason why, do post it in the chat. I think we have moderators who will look into it and let me know. Comets are very interesting objects. So the objects which I've described till now have typically a circular orbit around their host. So moon has a typical circular orbit around the Earth, and the planets have a typically circular orbit around the sun. But the comets are the ones which have a elliptical orbit. What it means that a sun is, it comes very close to the sun and goes very far away from the sun during its orbit. A great example of it is Halley's Comet, which takes 76 years to move about the sun once. And it only stays close to the sun for a very short duration of that 76 years. And when it comes close to the sun, it shows spectacular tails, as you can see in this. So this one is a comet which was pictured very recently. It is comet Neowise, and it was taken by a astronomer at Aries, and it was selected for the best picture for the best picture of comet Neowise by Astronomical Society of India. So these comets are icy rocks, and they basically show they are basically the source of what we assume that they are the source of water on Earth. And one of these comets crashed long back and delivered water to us, and that's what we have assumed. And we can't prove it because we can't go back, at least not conveniently. So this is so these objects are our neighbor. They are in our neighborhood, and they show interesting variations across the time, across the year. So, but this is not the only thing which does change across the night sky. Some of the most interesting changes which happen in us, which happen, are outside our solar system, and they give us very interesting information about those systems. So before I go into that, I'll ask you a question. So the objects which I've described are typically varying on days, weeks, and months, and maybe years. But can things vary at short time scales? Let's say an object which is as big and massive as a sun becoming brighter or dimmer in less than a day. What about less than an hour, less than a minute, or even less than a second? You can think on it, and if you get an answer, you can post it in the chat, and then we and be, please do that before I go into that topic so that you don't cheat. So, so one of the example is one of the stars which we see in the night sky. In old times, people used to imagine that the sky is imprinted with characters in from their mythology, and they divided the sky into these characters, and thus they marked out constellations. So I've given an example over here. This is the constellation of Perseus. So Perseus was a Greek demigod who killed a monster called Medusa. And in the imagination of the ancients, Perseus is standing in the sky, holding the head of Medusa in his hand. And as you can see over here, and one of the stars, which is marking the Medusa, is Algol, and it corresponds to the eye of the Medusa. This star is actually very interesting because it shows a change in its brightness over a 3-day period. Now, and since it is corresponding to an eye, people thought that this demon is looking at them and blinking and trying to curse them. With better observations and current model of the stellar dynamics, we now know that this is due to the eclipse of the star. So what is happening is there are two stars in the system. One is a brighter one and one is a dimmer one. So when the brighter one goes behind the dimmer one, which happens over here, what happens is you get a sudden dip in the brightness. While if the dimmer one goes behind the brighter one, you get a smaller dip in the brightness. And when both of them are visible together, you get a similar level of brightness. So that tells us that this system is quite an interesting system. So using just the observations across different days, we can determine that there is a star there are two stars which are rotating about each other. One of them is brighter than the other. And if we study this dip in more details, we can determine what is the radius of the star, what is the luminosity of the star, what is the mass of the star in more details. And this is the kind of work which astronomers have been doing since ages. And this system is a very particularly interesting system because it gives us a view of edge-on system. And we can have different sets of inclination, which tells us about different physics as well. Let's check out a different kind of variability. So this was a variability which was occurring due to a motion. But what if the star itself is variable in some sense? So there are certain kinds of stars known as Cepheid variable stars. So what happens is the star itself is showing an oscillation. What it means is that it goes brighter, dimmer, and then brighter again. And the time it takes to go from bright to dim to bright again is related to the mass of the star. And the mechanisms which cause this brightening and dimming are related to a particular chemical composition of the star, which combined with the mass of the star will tell us the brightness of the source. Once we know the brightness of the source, we can determine what is the intrinsic brightness of the source. We can determine what is how far the source is. To give you an example, consider you have a 100-watt lamp which is placed, let's say 10 meters from you. You will see certain brightness, some amount of light from it. Let's move that lamp 1 kilometer away, and you can determine what is the brightness from it. And if you now compare the brightness from 10 meter away and 1 kilometer away, you can guess that the brightness falls off as 10,000 times, because your distance increased by 100 times. So this kind of simple calculation can tell us that if you have a star whose brightness you know accurately, and if it is a particular distance far away, then you can determine what distance it is to be visible at the brightness you actually see it. And thus, this star can be used as a scale for the universe, which is very important because we would like to know how far away things are in our universe, how big our universe is. So this is one of the steps in what is known as cosmic ladder. I'll get on to another step soon. So in my first slide, I showed an image of a lighthouse. The sky has many lighthouses of its own, but sadly there are not that many sailors which are trying to roam about. So these lighthouses are most commonly seen in radio bands, and so radio waves are the one in which we see, in which our cell phones are connected with, and probably you're viewing this live webcast on. What we see is that for a short amount of time, there is a spike in the radio waves, and then there's nothing, and then there's a spike again. And this continues on and on and on. And this happens with such a precise frequency, we can determine that it's a spinning system, which is not being perturbed at all. And this whole spin of the system is happening for a very short duration of time. It's happening in a very short duration of time, like a few seconds, and in some cases, less than a hundredth of a second. This happens because what we have is a neutron star, which is at the center of this system, and it is emitting radio waves from a very small region on its surface, and it is spinning very fast. Like for an example, like a spinning of a lighthouse bulb. And whenever the region is pointed toward us, we see that light. And so here is an example of one of this system. This is a what is known as Crab pulsar. It spins at 130 at the 1/30th of a second. It spins once in 1/30th of a second. And this star is a remnant of a supernova explosion. The mass of the star which is left is quite close to our sun, but the radius of the star is mere 10 to 15 kilometers. Just imagine a star as big as a sun, which is being compressed into a region which is smaller than the city, let's say Pune. From these beacons, we not only see emission in radio waves, where we see this blip and nothing, we also see emission in optical light, the light which we can see, the light in X-rays and gamma rays. X-rays are the ones which doctors use to check on our bones, and gamma rays are the one which is very dangerous and come from the nuclear power plant. So I'll move on to something which is particularly close to my field of research, which is black hole transients. So what are transients? Transients are events in the sky which happens for a very short duration of time, and then poof, nothing, back to normal. These include a variety of stuff. But what I work on is black hole transients. These are very peculiar systems. So what we have is a black hole and a normal star which are rotating about each other, as you can see over here. The black hole has to be, for them to be a transient, the black hole has to be quite close to the normal star, and it should be able to pull the matter from the normal star onto itself. This pulling of the matter is also known as accretion. And as the matter accretes towards the black hole, it forms a disk-like structure, which is something similar to the rings of Saturn, but not very like that, because this disk is very hot and it emits in X-rays, while the rings of the Saturn are quite cold in that sense. Now these sources can suddenly brighten up, and then they can be seen by our X-ray telescopes. During this phase, which is also known as outburst phase, we get to see unprecedented details into the source. The black holes themselves don't emit any radiation, but if we probe the regions around the black hole, we can actually get what is happening close to the black hole and thus understand your black holes very well. The variability in the system also indicates that, yeah, the variability in the system also indicate that what are the changes which are happening very close to the black hole and at how fast those changes are. Only recently we were able to look at one of the largest black holes in the center of a galaxy far away, and we still cannot probe the details around it visually. So we need to look at the variability of the system to understand what is happening around them. Another type of transit which occurs is the death of the star. Massive stars die spectacularly. They die with a big explosion called a supernova. When these stars die, they become so bright that they outshine a galaxy. Over here, I have shown a supernova which happened in 1987. I wasn't born there, but it was quite a big deal then. A particular kind of supernova, not this one, is called supernova type 1a. That supernova is based on a white dwarf which is accreting matter and then blasting off. That this process is unique in the sense that for all the white dwarfs, it happens in a similar way. So if you see a type 1 supernova, you instantly know what is the brightness of that. And once you know the brightness of it, you can determine how far away it is, just like your Cepheid variables. And this becomes the next step over the Cepheid variables to probe into the depths of the universe using supernova 1. Well, I have shown earlier that there are systems which revolve around each other. So let's see what happens if there are two compact objects which are revolving around each other. So what happens is, if they are compact objects, they can come actually much closer than bigger systems. And once they come very close, they collide. And when they collide, they emit gravitational waves, and in the process, they form other different types of supernova as well. And in this process of supernova, you can see heavy elements are also formed, which is probably the source of all the gold which we have on Earth. So we'll have to thank colliding neutron stars for the gold which we have. And yeah, so another kind of interesting burst which we see are using gamma ray telescopes. Using gamma ray telescopes, we see regularly bright flashes of light which typically last for a few seconds. In the duration of this, the object emits the energy almost equal to the output of 1,000,000 suns, which across the duration of the life of the sun in a few seconds. Thankfully, this bursts happen very far from us, and therefore we only see a glimpse of the radiation, and only if it is pointed towards us. But even in this glimpse, we can decipher a lot about these systems. And these bursts are also known as gamma ray bursts. So, all in all, what does the variability tell us? So, using the variability, what we have determined is what is the motion of things around us, and that how can that be used for keeping time. There's an interesting talk on timekeeping which is for after my talk, so please stay tuned to listen to that. Secondly, a particular peculiar pattern of variability seen in different stars or in and around galaxies can be used to measure the distance in cosmos and figure out how far away things are happening around us. Then if we see something varying, we can study those variations and figure out what is happening in the source, even if we don't directly see that source. And lastly, if we do see some transient, a quick look there can tell us what happened there and how does that affect us in the future. in a broad term scale. So thanks for listening. And if you have any questions, please post it on the chat and someone will filter it out for me as well. And do check out the posters about the work which we have done at IUCAA. And my colleagues will go into more details about some of the stuffs which I've mentioned in my talk. Thanks.
Thank you so much, Yash, for bringing to us this talk. It was quite exciting, and I'm sure that students here enjoyed the talk as much as the pictures that are there, because astronomy is also so much about this.
Yeah, at one time searching for those pictures.
Yes, so that's great. We enjoy searching and sharing with everyone. So thanks for taking that effort and making it such a lovely talk to look at, and of course to get a lot of information. And in fact, like people were asking, what is this variability in the sky? Does the sky vary? And it's great to know that it varies in so many ways, right? From things like the moon will change apparently, not really, but then there are actually changes happening in the sky.
Yeah.
We have some questions on the chat, and I'll quickly look at if there are any relevant ones which are coming up. Just give me a minute. Yeah. In fact, so while people still type their relevant questions, there are a few questions which can be which are more fact kind of things. So Prajal Ghosh is asking, when can we see the Halley's Comet again in the near future? And if you want, I can also help you.
Yeah, you can answer it, because I wasn't born when the comet occurred, so I don't actually.
Right. So Halley's Comet actually has a period of about 75, 76 years. Yeah. And it came last in, I think, 1981 is what I think it came in. So the next predicted coming of the comet would be in 2061 in July.
Yeah, it'll be very old.
So yes, you keep a lookout for it, Prajwal, and hope we will also be there to see it.
But there are very interesting comets which we can see now. So
sure,
you should check out the comets that are being seen currently. Neowise was very bright and very interesting to see because it had two tails. So
right. And these make like really good spectacles for astrophotography, as we just pointed out.
Yeah, exactly.
And in fact, some people relate comets. There are these other kind of relations, human psychological relations. So people relate variations in the sky with various things happening on the Earth. So they might relate with daily life things like tides, etc., are directly related. But some people try to put a relation between variability in the sky and your own life. Not all of them are related, of course, but people try to find this relation. So with comets, many people say that they bring earthquakes and floods and things like that. Let us assure you that that does not happen. And at any time of the year, on any day, there are about 5-6 comets up there in the sky. Only thing is you cannot see them with your naked eye, but doesn't mean they are not there. And if they were bringing all these calamities, they would be happening every day.
Exactly.
Right. Now, this is about, again, about seeing with your naked eye. There's a question by somebody called Wacky Scientist, and he or she is asking, was the 1987 supernova visible in the night sky? Or if you could, like, if you
I think it was visible.
I'm sorry?
I think it was visible and it was bright, but I'm not sure.
Yeah, so I'm just quickly checking the what is called magnitude of it, and magnitude was about 3. So maybe, I mean, for people who looked at it with binoculars or so, might have been visible.
Yeah, 3 is visible, I guess.
Yeah. So
sky it is visible. Yeah.
It was in the southern skies, so we won't see it from India.
Yes, of course.
Magellanic Cloud. That's right.
You can always take a trip to South Africa, for example.
The remnant is still there, and people are following it up.
Remnant is still there, and people are actively researching on it.
Right. Great. So, any aspiring scientists here could actually get involved in this research, because the supernova evolves over many decades and it's still evolving. So, not just
still evolving, it is providing an interesting wealth of information about what all can come out of a supernova. Right. Like what all elements can be created out of supernova, for example. Right. Dynamics of the cloud which is going away from the star and whatnot.
Right. So yes, it's still an exciting object, and there are several such objects which are changing over time, and their light is changing, and you can find out details. Please refer to Yash's talk in case you're just joining in. Just rewind after some time, listen to the whole talk. It's been really eye-opening to see so many kinds of variabilities in the sky. One more question. I'm not sure who is asking that, but how do we differentiate between a Cepheid variable star and a binary star? So,
okay, that's a very interesting question. So Cepheid variable stars, the shape of the variation is a bit different from the binary stars. So I didn't show a variation plot of the Cepheid variable stars, but I did show the variation of a binary. So in binary, what happens is you will see a dip in the light curve whenever there is a blocking of the starlight. So that corresponds to a dipping feature. But in a variable system, it will smoothly go up, smoothly go down, and smoothly go up. There won't be any period of rest. So it will be continuously varying. So that is a sign of a Cepheid variable star, as compared to a binary system where you will have a period of rest when both the systems are visible in that sense. And this binary variation is only possible for ecliptic binary, in which you can see eclipsing of the system. This is not true for other types of binary systems, which show only changes in the position of the star.
okay.
So there are different kinds of binary system as well. I didn't have time to go into detail of that, but yeah. So that is what I would like to say.
Okay, sure. I think your talk also mentioned novas, and so there's a question from Bhagyashri Kachre, who's asking, could you say something about the kilonova explosions that she has heard of?
That's a very interesting topic. So kilonova is a milder version of supernova in some sense. So so what happens is so kilonova explosion is the explosion which we see when there is a merger of two neutron stars. So if you remember the video which I showed for merger of two neutron stars, there was a bright yellow light. So that yellow light is corresponding to the kilonova emission, while supernova is typically due to a death of a star. But there are more interesting, like a better explanation can be found in one of the posters which we have for the display in today's session. So I would suggest you to have a look at that as well, because that will explain you in more detail and with more precise numbers.
Yeah, just looking for more questions. We are actually coming close to the next speaker's time.
There is one more question, Samir. The question is asked by Ishwari Zamdar, and the question is sun included in any of the constellations which we can see from other planets? So as Yash had mentioned about pictures, the zodiac signs and constellations. So maybe you can answer that question.
Okay, so constellations are a very funny and interesting business. So what happens is constellations are defined from Earth. So as you see the sky from Earth, you can define the constellations. At least if you go into different planets in our solar system, you wouldn't see much change because all the stars are really far away. But if you go to a system of a different star, you would see different sky altogether. So the constellations defined there and here are different in that sense. So I guess the question was that if you see a constellation from a different planet, do you see sun as a part of constellation? Probably, because if you go to a different star, sun will be somewhat like another star for that system. So it will be part of that constellation. But from our solar system, sun is actually a much more resolved star. So you won't put it in a constellation. Plus, it moves about so much that you cannot fix its position in the sky. And constellations are typically fixed in the sky,
Okay.
at least for human lives.
All right. Yes. So that's great. I mean, I think there might be several queries coming up during the rest of the day, and we can handle them during the poster session. But thank you for this excellent talk and bringing us to this lovely looking talk, actually. So let's thank the speaker again, everyone here, and we move on to Professor Shubhadeep De, who is here to talk to us about the new technologies being used in research in astronomy, astrophysics, although they sometimes seem to be not related directly. So it's probably, if you're not building a telescope, people will think that, you know, how is it related to astronomy? So he's going to present to us how clocks are important to astronomy. So clocks have this unique, you know, role in human life. They define our time. The way we use time is coming from the presence of clocks. The evolution of measurement of time has an amazing history. I think Professor Shubhadeep will present that to us. But it's also important that we realize that the measurement of time kind of came to us from observations of cycles in the sky. Some variability that Yash had just mentioned. So we have variability in the sky, and that is kind of what led us to the understanding of passage of time. And also led us to keeping time, like we need to know when it is day, when it is night. Also, we need to subdivide the parts of the day. So clocks are very important in our lives. We always look at the clock before going out. What is the importance of clocks in astronomy? And we will be looking at such questions with Professor Shubhadeep. So if you could see you, Dr. Shubhadeep, we would also probably like to chat with the audience a little bit about your journey into science and how you came to research in this field.
Hi, Samir. Thanks. Am I audible?
We can't see you. You're audible though.
But I'm not able to start my video for some reasons. Do you need to do something from your side? In fact, I'm not able to share my screen also.
Okay. We're just getting to that. Yes, these days, all sorts of things are online and there are several technical parameters. We're just setting them right.
Sir, can you retry now?
Now, actually, it's completely like gone into non-working mode for some reason, and I'm not able to control anything. Can you quit me maybe, and then I can rejoin, which may work sometime?
Yes, just a minute.
Because I'm not able to quit myself.
Okay, we'll do that. But that while that is happening, as I was saying, that time has a very important part in our life, and astronomers not just look at things which are in the sky; they see their variability, and these tell us a lot of information about how the mechanisms of those things, those phenomena, or those objects are there in the sky. So we'll be looking forward to this talk very soon. Let me tell you, in the meanwhile, while we are waiting for people to kind of figure out this technical glitch quickly. Yes. So we have a lot of other programs lined up, and soon after this, we will have two talks, one by Professor Neeraj Gupta about the Square Kilometer Array, which is one of the largest telescopes which looks at radio waves coming from the universe. And no, radio waves do not just come from aliens. In fact, they don't come from aliens at all. We've never had any alien contact yet. And but they are very important to understand a lot of low energy and high energy phenomena in the universe. So that's coming up at 12. And at 12:40, we will have Professor Ram Prakash speaking about one of the most important projects which India is part of, including, of course, the Square Kilometer Array. But India is also part of the 30-meter telescope project. Just the name would tell you that it's going to be an eye which which humans make to look at the universe, and this would be 30 meters across. It's just the eye is 30 meters across. So just imagine how big the whole telescope would be, around 5 stories high, and it will give us a look at the universe at unprecedented level, right? With the special technologies which will be used in it, I think it is going to be one of the most look forward to projects in the coming decade. And India is part of it. IUCAA is part of it, along with Indian Institute of Astrophysics and ARIES and Nainital, which is another astrophysics institute in the north. So we are all looking forward to this talk to see about what is this project and how we can be part of this, because this project, the 30-meter telescope and the square kilometer array, which India is part of, plus Professor Shubhadeep Dey, who will just be coming online and presenting to us his work on atomic clocks. These atomic clocks are actually going to be used in a very important project called LIGO India. So this is the laser interferometer gravitational wave observatory being made in India, in Maharashtra, at a place very close to in the Hingoli district actually. So this project is also there, and therefore you can see that it just in this coming decade we have 3 major projects in which India is part of. Okay, so at earlier times it might have been a concern that okay, okay, fine, I become an astrophysicist. Now where do I go to work, right? Which country should I migrate to, etc. You can see astronomy, astrophysics is an international subject, it's a global subject, and all people collaborate to work on this. But of course, if if things are closer by, it's easier for everybody because there are other things in life that people think of. So if you have a closer by project, you would probably be happier to work on it. So these projects are allowing Indian students, Indian researchers to work from their own country's soil, okay, and be part of some of the biggest projects in the history of astronomy. And so I think these are going to be monumental projects, and they are something we are extremely proud of, and also looking forward to all of you joining. So this session that we are having here, we are looking at informing you about these projects, and of course also how you can be part of something like Square Kilometer Array, 30-meter telescope, and the LIGO India project. So keep looking, keep watching the webcast, which will happen over the next few hours. And we are back with Professor Dey here, who's going to present to us this lovely journey from sundials back when there were hardly any electronic tools or even mechanical tools were not there to measure time, to atomic clocks, which are the most accurate in this world. Professor Shubhadeep, are you okay with your technical?
Yes. I hope I'm audible now.
Yes.
I'm also visible. Okay. So shall I start my talk?
Yes.
Thanks.
Let's do that.
Thanks, Amit. Thanks for the introduction. Okay, so good morning, everyone, and sorry for this inconvenience. What has happened? It's just a technical glitch, so I had to go out and rejoin again. So sorry for it. So yeah, so let me start. I'm going to talk about the journey from sundials to an atomic clock, and particularly why do you need at all the atomic clock? I mean, this is so accurate, one of the most precise machines that mankind have ever built, which can measure time with an accuracy of 1 second over the period of, let's say, age of the universe, which is 13.8 billion years. So why do we need that kind of clock, and what is the mechanism that's behind the atomic clock? So I'll talk about that. So the title I have chosen for that particular reason, so that I can tell you the journey, but otherwise there is another reason. At IUCAA particularly, there is already a sundial which existed since the probably starting of IUCAA, and that's the picture what you see here. It's in the science park, and now IUCAA is going to build an atomic clock. So that's also a journey, like from IUCAA's own perspective, that going from sundial to an atomic clock within its own laboratory. And below you see the picture of IUCAA, the Kund part of the IUCAA. So let me start. So when we talk about clock, for any clock, either it is a sundial, or it is an atomic clock, or it is a pendulum clock. Basically, clock have.
We need to see your slides, so we are just seeing your camera.
You are not seeing my slides?
Yeah, so let's quickly.
Can you share your screen, Subhadev?
Yeah. Do you see it?
Yes, now we can see.
Yeah, now.
Maybe
Okay.
go a slide or two back and start.
Yeah. So I hope you heard what I said in the first slide. So there is nothing more to say. So I'm going to the second slide, and let me start with the very basic, that what is behind a clock, irrespective of whether it is a sundial, or it is a pendulum clock, or it's a quartz clock, or an atomic clock. Basically, the basic principle is same for all kind of clocks. And a clock has two parts. One is a periodic oscillator. The oscillator can be of different kind, like either it's an atom, or it's a pendulum, or it's a sun moving around earth rotating, so that you can see sun sometimes coming up and sometimes sunset, etc. But this is some periodic event which you need to make a clock, and you need a process to count that periodic events very accurately. So let's say if you have a pendulum which is oscillating once in every second, so you need a mechanism to count that every single oscillation very accurately. So if you know the time period of each oscillations, then by counting the number of oscillations, multiplying these two things together, you can say what is the time duration, right? So for any, and then finally, once you do all this mathematics, it's getting displayed in a display, whether either it is a mechanical display or it's an electronic display, depending on different technologies and so on. So basically, to make a more accurate and very precise, or let's say stable in another way, clock, you have to have a very repeatable oscillator, so that the repeating period is not changing over a very, very long period of time. There is no frictional change or anything like that. And you need a very good counter, so that there is no error in counting this number of oscillations. As you can do better and better in these two things, you can actually make better and better clocks. So just I am giving you a few examples of clocks from ancient Indian history, which is basically more or less same in everywhere in the world also, but I picked up the pictures from Indian history only, just to tell you that our ancient science was very strong, in fact, like anywhere else in the world. So in the Indus Valley civilization, people were using the water clock. So there you have a very big jar of water, a reservoir of water. Then you take different size of bowls with a small hole at the bottom, and you was putting these empty bowls on the reservoir of water, and then slowly the water will be filled up inside these bowls of different size, and it will take some time before the smaller bowls will sink into this big reservoir. And that was actually measurement of a like an oscillation period. Let's say it's a periodic event, and you can take a estimation of time, or time span, basically. By the way, whenever we are talking, whenever we say time, it's actually not the absolute time, but it's actually the time span. It's like the time difference between two events, and that's what we generally call time, but it's actually time span all the time. There is no like absolute time. The absolute time starts from the Big Bang. And then later on, it was a sundial, and there are several sundials in India, starting from the sundial in Konark. Then Maharaja Jai Singh, he built 5 sundials in different places of India, starting from Jaipur, the Jantar Mantar, and then also Delhi has one Jantar Mantar, and then Varanasi, then Mathura and Ujjain. There are the 5 places where he built Jantar Mantar, which have sundials as well as different other astronomical instruments for to study astronomy. And here you see 2 pictures, the Jantar Mantar in New Delhi and Jaipur. So in ancient ages, there was also units of time. Like for example, today we use the international definition of time is by second, and then by minutes and hours, so on. In our ancient ages, the smallest unit of time was nimes, and nimes is basically the time you take to blink your eyes or eyelash, and that is typically 200 milliseconds. And then with the smallest unit, there are bigger units which were also made, which are listed here. I'm not going through all of them. I'm not going to read all of them, but few of them you can actually correlate very easily. Like for example, ahoratram or muhurta, we still use in our rituals like muhurta. So that was actually one of the ancient units of time in our Indian history. Then masa is month basically. Then ritu we obviously know, and then 6 ritus were samvastra, so it's like 1 year, and like that. So in 1967, this measurement of timekeeping was changed on the basis of atomic clocks in an international standards. And in 1974, first time India acquired an atomic clock from US, and that was in the news. NPL, CSIR National Physical Laboratory in New Delhi, who actually is timekeeper of our nation, who maintains the Indian Standard Time. They acquired atomic clock, and it came to the news. And another thing I would like to point out, since then, the Indian Standard Time is maintained by using the atomic clocks, and the Indian Standard Time is basically the line which goes through a place in Uttar Pradesh called Mirzapur, and that is actually the Ghanta Ghar picture of that particular place, which is a reference of the Indian timeline or time zone. The entire country is considering only one time zone, that is UTC, Universal Coordinated Time, or let's say same as for layman's, it's same as the time at 0 degree longitude at or GMT plus 5.5 hours. So we are 5.5 hours ahead of UTC, and the entire country follows that thing, which is maintained by the National Physical Laboratory. So far so good, using the atomic clock, of course. Now, why? I mean, I already told you about different kind of clocks, starting from the water clock to sundial to an atomic clock. So how, the question is how these accuracies are being better and better in different kind of clocks. What is different in this case? So the point is, if you take the oscillation period very faster, so let's say you have a pendulum which oscillates once in every second. Instead of that, if you take a pendulum which oscillates 10 times in a second or 1,000 times in a second, then you actually can be you can actually make a better and better clock with faster and faster oscillators. So as you see, this Allen deviation, which is actually measure of the accuracy of a clock, which is inversely proportional to this oscillation frequency, that is nu naught. So in case of a pendulum, this nu naught is basically just like 1 oscillation per second. In case of an atomic clock, this is 10 to the power 18. Sorry, 10 to the power 15. Yeah, 10 to the power 15, 10 to the power 14 to 10 to the power 15. So since it's inversely proportional to this nu naught, if you take faster and faster oscillations, you can actually make more and more accurate clocks. And why that is the case, you can understand it very easily. Let's say you have a oscillator which oscillates once in every second. Then if you miss just only one count, then basically you are missing one complete second, right? But instead, if you have a oscillator which oscillates 1,000 times per second, and in that case, if you miss one count, then you are missing only 1 millisecond, right? So you are basically making a better clock. And in this case, in case of an optical atomic clock, this is oscillating 10 to the power 15 times per second. So if you are missing only one count, you are basically missing only 1 femtosecond, something like that, right? So that's the reason faster the oscillations, you will get better and better clocks, and that's what is said here in the rest of the slides. And in case of an atomic clock, so far we work in 2 different areas of the electromagnetic spectrum, that is the transition frequency of the atoms. One is microwave frequency, that's around 10 to the power 10 hertz, or let's say around 10 gigahertz. And in the optical clock, this is in the optical wavelength, optical frequencies, and that is on the order of 10 to the power 14 to 10 to the power 15 hertz. This is like visible and near UV wavelengths typically. And for the practical purpose, actually. I mean, we don't have a laser in very deep UV or very deep X-ray, something like that. That's the practical reason. So far, we are able to measure or develop the optical clock within this regime, and that gives orders of magnitude better and better in terms of the clock's accuracy. So over, let's say, last several hundred years, here it is like around 700 years, like this picture is saying how the accuracy of clock has changed from a very basic and primitive clock to the most advanced atomic clock. In the x-axis, you see here the years, like from 1300 to until now almost, and the y-axis, it says the duration of a clock operation over which that clock particularly says 1 second of inaccuracy. Yeah. So you see the early mechanical clock was very much inaccurate, like over 1 minute, it was almost inaccurate to 1 second. Over just in 1 minute time window, it will give 1 second false time. Whether at this moment, we have the optical atomic clock, which can run over, like, the base clock, actually, if I put it into the proper number, over 34 billion years, it can give only 1 second of false timing signals. So it's much more than actually the age of the universe. Sometimes people actually do mistake when I say these things. So they consider that there is already a clock which is running from since the beginning of the universe. No, that is not the correct thing. It's an assumption. Like, if you just to put it for the general public so that they can understand, like, supposedly there was a clock which is running for last 34 billion years, then it will give only 1 second of false signals. That's what it means. So in principle, there is no such clock which exists. So now let me transfer to the atomic clock. Why do we need an atomic clock? Why? I mean, of course, one reason I already told you, that is, like, the atomic clocks, the oscillation periods are very smaller, or the oscillation frequency is very faster. And as you go to faster and faster oscillations, then you can build better and better clocks. So unprecedented accuracy can be achieved using the fast oscillations of an atomic clock. Otherwise, there are actually novel techniques which have been developed over last 30-40 years, that is called laser cooling and trapping, and also ion trapping, if you talk about ions, or if you talk about neutral atoms. Then by doing that, you can actually confine few atoms, or even actually single atom, in a very small volume. The volume is like so tiny, it's like a few microns or few tens of microns. In that small, very confined volume, you can trap one single particle or single atom, and you can do the further experiment with that. The advantage, and also not only trap, you can also cool the atoms to almost 0 degree Kelvin. Absolute 0 degree Kelvin is not possible, but very near to 0 degree Kelvin, like 90 pico Kelvin or few tens of pico Kelvins has already been achieved. And what happened by doing that, once you trap these things in a very small volume, you can actually characterize these things very well, and you can reduce many systematic errors which plays role for this kind of precision clocks to enhance the accuracies faster. So it's basically, in a simple words, it's almost perturbation free. By doing this, by implementing these techniques, you can create a environment which is almost perturbation free, and then you can measure these transition frequencies very, very accurately, and then build a very precise or accurate clocks. So at present, the international definition of time is based on atomic clock. It's based on cesium atomic clock, a particular magnetic dipole transition of cesium atomic clocks. That is the cesium ground state, and it's splitted. It's doubly splitted. It has like two hyperfine sublevels. F is equals to 3 and F is equals to 4. F are the quantum numbers, and the transition frequency between these two states have been measured very, very accurately with an accuracy of 100 millihertz, even better than that. And the transition frequency is 9192601770 in terms of hertz. It has been measured after decimal point also. And that means this many number of oscillations, this 9192631770, the time required for this many number of oscillations is international definition of 1 second so far. And there are two type of cesium clocks. One is cesium beam clock, which uses the normal temperature atoms, room temperature or slightly above the room temperature atoms. And the most precise cesium clocks uses the laser cooled and trapped atoms, where the atoms are at 100 microkelvin temperature, and there you can get the best accuracy of on the order of 10 to the power minus 16 or so. So basically from beam clock to fountain clock, it's almost 2 orders of magnitude better in terms of accuracy. Let's see how the beam clock works. Let's say you have a reservoir of cesium atoms, so we call oven, and if you heat it up, and if there is a small orifice, the cesium atoms will come out through that small hole and it will go through. Then it passes through two stages of magnetic gradient, magnetic field gradient, to apply the Stern-Gerlach effect. So this is the first stage, and this is one stage, and in between there is a microwave cavity where we apply the microwave, or this 9.192601770 Hz. That's the microwave. We apply that microwave and we transfer the atoms from ground state to the first excited state of this hyperfine sublevels. So what happened in this first Stern-Gerlach stage? I mean, the cesium atoms, to start with, they are divided equally into two states, F is equals to 4 and F is equals to 3, 50% in the upper state, 50% in the lower state. But we want to have a state selection, so all the atoms are in F is equals to 3 state to start with, and that is happening in the first Stern-Gerlach state, so that we do a state selection. Then once we select a particular type of atoms which are at F is equals to 3, passes through the microwave cavity, and if we don't apply a microwave, or if we apply a microwave which is not at the correct frequency, nothing will happen. You will not see these atoms coming through the detector. But if you apply the correct microwave, then in the second, so then atoms will transfer from F is equals to 3 to F is equals to 4 state, and then what happened, that will be affected by the second Stern-Gerlach state, and it will be bended in a proper right direction, so it falls into the detector and you will get an alarm. That's the technology of this simple technology of the cesium beam clock. Well, it's not also that simple, but it's simpler compared to, let's say, at a fountain clock or optical clock. And by proper tuning of the frequency, you can measure this exact frequency very accurately and very well. Then you can convert it into time domain, etc. Now I'm coming to the next one, that is the fountain clock, where people use the cold atoms, not the hot atoms, not the atomic beam, but they are collected. This is again the oven where the atoms are coming. They are collected by a technique called magneto-optical trapping. I'm not going into that technical detail of this. That will take longer time. Once it is collected, an ensemble of the atoms are pushed upwards. That's why it's called fountain, upwards through this microwave cavity, and then they reaches at a certain height, and then after that, due to gravity, it falls back through the same microwave cavity. And since it's passing through the microwave cavity twice, there are some phase acquisition happens, and that produces an interference pattern, and that interference pattern is detected by shining a light, a proper laser light, onto the atoms, and that's what is shown here. And then this is the complete picture of the fountain clock. So it's like collected first. This is the collection of the atoms, and then laser cooling to tens of microkelvin or hundreds of microkelvin temperature, then pushing it upwards, then it falls back again to the same cavity, and then it's detected. And by that technique, the accurate frequency, this 91926317770, is detected very, very accurately. And the enhancement, see, basically you are detecting the same frequency, but the further accuracy comes because you are lowering the temperature of the atoms to almost like below a few hundreds of microkelvin temperature. Many of the systematic effects becomes almost negligible, almost cancels out. And second thing is, like there is, which I did not go into the detail of that thing, like it's a Ramsey spectroscopy. So you can narrow down the spectroscopic fringe width, and then you can measure this frequency very well. I did not go into that particular detail, which is due to the time, but basically that's how the enhancement of the accuracy comes in this case, and we can do much better diagnostics of that frequency. So now I'm coming to the second part, which is the optical clock. So far I was talking about the microwave clock. Now I'm coming to the optical clock, which works in the optical domain, and that is particularly which we'll develop also at IUCAA. And there are two different kind of optical clocks. One is the lattice clock, and other one is the trapped ion clock. And here are the two different types shown like schematically, and two pictures from two different labs in the world, PTB in Germany and Chile in USA. This is a strontium lattice clock, and this is a trapped ion clock. In this case, neutral, in optical lattice clock, the neutral atoms are confined or trapped, and then at a particular optical transition, it's been excited and it's detected and the clock is being made. But in case of ion clock, it's a single ion which is trapped in an ion trap, and then particular optical transitions, which is we call clock transition, is being detected. So this table actually gives the accuracy of atomic clocks, microwave as well as optical clocks so far, which has which becomes more and more accurate until now. And you see, in case of optical clock, both of them have reached to a level of very low 10 to the power minus 18 or 10 to the power minus 19 level, which transfers to 1 second accuracy over age of universe. It's in fact actually much more than age of universe. That's what it is. So far, this SI standard of time is based on the cesium clock, and it is expected soon, maybe in 2026, that the definition will be changed and it will be done with respect to an optical clock. So for time and frequency metrology, there is an important importance why we need to build an optical clock. But otherwise, other than the time and frequency metrology, for basic science, to study basic science, optical clock plays a very important role. This is one way to take forward to measure something, measure few of the things very, very accurately. So there is a science aspect also other than the time and frequency metrology. So here I have listed few of the things why we need precise clock or precise optical clock. So the first thing is from the time and frequency metrology perspective, like navigation purpose, communication, electronic transactions, strategic sector, cyber security, and so on, which requires very precision timekeeping with an accuracy of like, let's say, even microsecond to much more than microsecond. So there, very accurate clock is, of course, obviously important. But otherwise, from the science perspective, that is what mostly we are interested at IUCAA. The optical clock is also very interesting, and the science are like looking into the temporal constancy of fundamental constants or fundamental symmetries, like electron to proton mass ratio or fine structure constant, or like violations of the Lorentz invariance violation, which is a fundamental symmetry, something like that. Then geodic measurements, also in radio astronomy, or basically in any astronomy, the array of telescopes, they are connected with very precise optical clocks and their phases particularly. So there are a lot of applications for very precise clocks. So now, if you see, since 1945, when the the atomic clock was first, the idea came from Rabi. It's the time of Second World War, I believe. And since then, how the atomic clock evolved so far until this, let's say, I kept it up to 26. Of course, I am sure there will be few more events in between. But 26 is expected that the SI definition of time will be changed. That's why I kept it at 26. Like you see, in 1955, cesium beam clocks was invented at NPL UK by SN and Perry, and then redefinition happened in 1967 based on cesium clock. Then cesium fountain clock was invented. Then in 2001, optical clock came into picture, and and then basically many things has happened in the optical clock and so on. And so far, the best fountain clock has achieved an accuracy of 10 to the power minus 16, whereas the optical clock is 3 orders of magnitude better compared to the fountain clocks. And so far, on different technologies that atomic clock is used, that has got 12 Nobel Prize so far, starting from Rabi to the recent one is Dave Wineland at NIST in 2012. So he built the quantum logic clock based on aluminiums and so on. That was his idea. The Nobel Prize was in a much broader sense and etc. But you see that there are, like, for example, Bill Phillips, he invented the laser cooling techniques. Bill Phillips, Cohen Tanuji, and Steve Chu, which is used in the fountain clock or as well as the optical clocks. Similarly, the other people like Hans Demelt and Wolfgang Paul, they developed the iron trap techniques. Yeah, so there are two kind of iron traps, Paul trap and penning trap. It was developed by these two Nobel laureates. So there are different techniques which atomic clock community is using that has got total 12 Nobel Prize so far until just recently in 2012. At the end, I just want to mention in one single slide that what we are going to do at IUCAA, we are going to develop an optical ion clock, single trapped ytterbium ion clock, and by using that, we want to do precision measurements and quantum metrology. And basically looking into this fundamental science aspect. I won't go into detail of that. There is, I mean, not too much time left over. So basically, I want to conclude that India has a very good history of clocks, starting from this water clock to sundials, and maybe, I mean, in future we'll be developing the optical clock at IUCAA based on this single trapped ion clock. There is our poster. You can also watch that thing, online poster. And thanks for your attention.
Thank you for this, Shivadeep. And we are basically have a lot of time and some questions also online. So we are looking forward to you interacting with the audience. And
Sure.
so I'll just read it up. Thank you, of course, for the very lucid presentation from you. I am just looking at the questions here. We have around 200 people watching right now, and some of them want to know. I think we can start with the questions pertaining to really early measurements of time, which you mentioned. So one person wants to know how accurate were the sundials when we were measuring time, with all the accuracy which is possible now.
Yeah. So sundials were actually very accurate. I mean, well, very means what is very, of course. But I mean, sundials has a different kind of varieties. There are very, I mean, from the early ancient sundials to, let's say, the recent sundials, there are many correction factors were taken into account. And once these correction factors are taken into account in the most recent ones, then it's very accurate. It's accurate to few tens of microseconds, in fact. Yeah, but tens of microsecond, when I'm saying it's a very accurate, it's actually not so accurate. I mean, let me give you just an analogy. Like if you want to place a satellite in a right orbit, a few microsecond is not good enough. Or if you like your Google Maps, when it works, the few microsecond time accuracy won't give you a very accurate position accuracy. So sundial is accurate, but not as accurate as we want.
Right. Yeah. So the other question is about the modern time. So what is I think what is a coordinated time and how is it kept worldwide?
Yeah.
About UTC.
Yeah. Yes, universal coordinated time. So earlier it was GMT, Greenwich Mean Time, and now it's UTC. So see, the GMT was based on rotation of Earth. Yeah, around the sun basically. So initially, so Earth has two rotation, around its own axis and around the sun. And initially, before, if I remember the year correctly, 1933 or so, it was based on rotation of Earth around its own axis. But then it was redefined as rotation of Earth around the sun. And GMT was based on Earth rotation. There is a particular international body called IERS, if I am right, International Earth Rotation and Something Society, who looks into the astronomical data, particularly quasar absorptions, and precisely determines how the Earth rotation is changing or what is the exact time period for the Earth rotation. And based on that, the time was kept. Like, let's say 24 hours in a one day. So 1 second is 1 over 24 times 60 times 60. That's the definition. Okay. But it's not very accurate because Earth rotation itself is changing very, very smallly over a long period of time as well as over a small period of time also because of mass distribution by volcano and many other effects. So it's not very accurate. So we need to have a separate timing systems which doesn't depend on Earth and anything, and that was atomic clock.
Okay.
Now there is a connection also we need from atomic clock to the Earth rotation, because finally we want to see what is the daytime, right? That's what anyone is actually interested. So that connection was done by IERS and the atomic clock, and IERS gives the correction factor that is introduced into the atomic clock things, and then it is UTC is generated. So if you just consider only atomic clock, then it is UT, universal time. Once this correction factor is included from IERS, then it is UTC, universal coordinated time.
So actually, there is a very related question, and since some youngsters are asking this, so what is this leap second which is added to UTC, and what is kind of any way that will be done next or something like that?
Yeah. So leap second is basically what just I told you, that Earth rotation is actually changing slowly, and it's actually becoming slower and slower, mostly. And once this slowness is such that we have to add 1 second or subtract 1 second, it's not that in every year we have to add leap second. It's over some time period when this IERS society says that you have to, I mean, there is a 1 second gap which you have to correct, then it is corrected in the UTC, and then that is actually leap second correction. And typically it happens in December. I mean, not necessarily it have to happen in December, but it happens in 31st December at the midnight exactly. In my lifetime, I did it once when I was at NPL. That was really a celebrating things that we added 1 second to the atomic clock.
Wow, wonderful. I was looking it up. So I think the last leap second was added in or whatever the period.
December, yes.
December 31st and 1st January 2017.
Right.
And it also seems that the Earth is somehow speeding up. So it's not so slowing down so much that we need a leap second. So for the last 1 year or so, there's been no leap second added. It's very, very kind of fascinating thing.
It depends on several things, like how the mass distribution is changing, where there is a volcanic eruption, where there is something else, and like ice breaks and etc. All these things, and various other factors also.
Wow, what a wonderful revelation about this. So there are more questions. One Diwan Daud wants to ask, are atomic clocks used for all scientific measurements or for some relevant ones, and which are they?
No, it's not used in all scientific measurements. That's not the correct statement. Like, there are some scientific measurements which directly uses atomic clock to do the measurement. For example, I mean, there are other techniques also, but atomic clock can also do that very accurately compared to many other techniques.
Okay.
Like, as I said, like temporal constancy of the fundamental constants or symmetries or geodetic measurements and so on. But there are other measurements which indirectly uses atomic clock to enhance their accuracy or sensitivity. For example, in radio astronomy, there are these telescope arrays. So all the telescopes, they are collecting the antennas, basically. They collect data from the sky at the same time. But how do you know? How do you correlate this data which are collected in different antennas? How do you say that this data is at the same time from that data of that, but another antenna? Okay. For that, you needed very accurate time synchronization among all these arrays. And now it was like, let's say GMRT, there are 30 antennas or 25, 30 antennas, but now it's going beyond the localization. It's like international radio telescopes are getting connected. So you need to basically connect all the antennas worldwide with a very precise timing signals and so on to compare the data which are collected in different continents.
Okay. Wow, that's you can see the utility of it. Rashmi Deshpande would like to know that why do we use only cesium ions and not atoms or ions of other elements?
Right, that's a very good point. The cesium atoms, first of all, it's not an ion, cesium atom. Okay. See, cesium atom has one particular isotope, 133, which is non-radioactive. For all other type of atoms, there are multiple isotopes which are non-radioactive. So in case you take any other atoms which have multiple non-radioactive or very stable isotopes, you need to first have to make a isotope selection.
Mhm.
Because from isotope to isotope, there is also a frequency change. If you want to measure this 91926317770, that would be different for a different isotope.
Mhm.
Cesium, by just naturally, it gives you that freedom. You only have one stable isotope, so you don't need to do an isotope selectivity in this case.
Okay.
That's the particular reason why cesium is there, and also it has the clock transitions and etc. But the clock transitions are there in many other isotopes, other elements also.
All right. Okay. So coming to the project you're involved with, LIGO India. So there are some questions specific to that. And one question is that, again, just to know, Parth the other day, I think he wants to know why is the accuracy of the clock needed for LIGO India, which is detecting gravitational waves.
Right. So that's what I was trying to explain. See, there are like LIGO in already 2 different places in US. Now there will be in US, and there are also Kagra and Virgo. So all these 5 detectors will look into the sky and will take the same gravitational wave, will detect the same gravitational wave. Now, the gravitational wave travels in the speed of light. So we know this spacing between, let's say, Indian detector to a US particular Livingston detector or Hanford detector, that spatial distance we know very accurately.
Okay.
But to detect the time, like whether we are detecting the same gravitational wave or detecting the same correlation, to make the correlation, we need to have a time synchronization among all the detectors.
Mm-hmm.
It's very similar to like for radio astronomy.
Right. Okay.
So that uses actually atomic clock, not the optical clocks, but that uses the atomic clocks.
Okay. And is there anywhere atomic clock is used in one particular detector, or is it more to coordinate between the detectors only?
No, I mean what they do at this moment, to best of my knowledge, they take the GPS signals, and then there are GPS receivers in every site, and they connect it.
Okay.
But GPS signal is not, I mean, let's say in futures, we need much better clocks than the GPS signal what you can go. GPS signal is based on cesium clocks.
Okay.
And when the time travels through the GPS, it actually becomes more inaccurate, like microseconds or something like that. Sorry, nanoseconds or something like that, few tens of nanoseconds and so on. In future, when you enhance your sensitivity, few nanoseconds or few tens of nanoseconds won't be enough anymore. Then you need a fiber optic connection between all these places, and that is actually already coming up.
Oh, right. Okay. That's great to know. I mean, the technology going into astronomy. We have one, I think we'll take one last question, and then I'll ask a personal question to you. So Mani Nair has a kind of futuristic question to us, that when probably he means to say that when we become a spacefaring race and go to various planets and all, so would we have a general space clock? And do you have any idea if such thoughts have already been given?
I mean, see, there are already space clocks. I mean, there are already microwave clocks in space. Every satellite have rubidium clocks. These are microwave clocks. It's very similar to the cesium clocks, but at a different frequency.
Okay.
So the next future generation, it will acquire actually optical clocks. So at this moment, only few countries have optical clock, few advanced countries. India don't have the one at this moment operating. The next thing would be to make it space qualified, means it should be a payload compatible. So it has to be miniaturized. Miniaturized means miniaturized in everything. Every detailed technology have to be miniaturized. People have already started working on that. Maybe, I don't know, 10 years down the line or even before that, we'll have the space qualified optical clock. And then these GPS things, all the clocks will be replaced by optical clocks, which will be much more accurate.
Okay. And so I think what he also wanted to know was, will there be a coordinated time, not just a clock, as that you answered? Is good to know that we have some clocks and they're going to be miniaturized. There's also a factor that the time will have to be coordinated. So it's probably what he also wants to ask is whether there'll be a coordinated system of time amongst planets. That will be needed.
That's an interesting thought, but I mean, obviously, I mean, if we are going to live in different planets, we have to have that. But I don't know if there is any thought at this moment. I mean, personally, I have no idea.
Yeah, I think going through some
But
science.
It has to be there. It has to be there. Yeah.
Sure. All right. So that's been a good interaction with you to know about clocks and their importance and the latest state of technology in timekeeping. But then we can't let you go without asking you your own journey into coming into science. So this event is all about inspiring the next generation to take up science and research. So could you share a few things with us on how you came to do all this?
Yeah, so actually, see, I mean, when I started my PhD or during my MSc levels, I was interested to do laser physics. And the reason why I wanted to do laser physics, it was like not very scientific reasons, but I mean, just before, few years before of that, there was a cricket World Cup match, and the opening ceremony was in Eden Garden, and then there was a laser show by Lunetta, some Italian persons who was showing some laser show, very nice one, and that is the first time I actually saw something laser show, which was so interesting. And from then actually I picked up that I want to do something with lasers if I do the PhD. And later on I got to know little more, and then I wanted to do this laser cooling and trapping techniques. But actually during my PhD and postdocs, I never worked with clocks. I worked with laser cooling and trapping and etc. But then clock is just one more application of this laser cooling techniques. So now actually, I mean, why I wanted to do the clock, because this is something has a national importance. I mean, you can do some basic research and etc. etc. You can publish a lot of papers which are nice, very good fundamental science. But in this particular case, or there are several other examples similar to that, these actually have a lot of applications in strategic sectors, in defense systems, in ISRO and all these things. And if you do a like this optical clock, that will be probably first time in India, or maybe few other will also come up, I don't know, but that will directly have the national importance. India will be at par to the international level. So that's the one reason one motivation that why I don't wanted to let's say start a BEC experiment, Bose-Einstein condensation experiment, which is my own expertise, particularly during my PhD and postdocs. But I wanted to come to clock things.
Wow, what an inspiration! I mean, from a cricket show to a researcher. That's great. And I can see that in your room you say, "My life is devoted to the safety, honor, and welfare."
Oh, you can read it really.
So thank you for doing this, and of course you're a part of IUCAA and taking forward this great project LIGO India with all the other colleagues. So thank you for being here and spending your time explaining the importance of clocks. Let's all thank him, Professor Shubhadeep Dey again. And now we move on to the next speaker, Professor Neeraj Gupta, who's from another important project in astronomy called the Square Kilometer Array. So, hello, Neeraj. Good morning.
Hi, Samir. Hi, everyone.
It's just past afternoon, like, the clocks. So it's just past the Indian Standard Time, noon. It's probably still to be noon in Pune.
Yes, Shubhadeep was accurately holding clock.
So thank you for being here. And we are all eager to listen to your sharings about the Square Kilometer Array project. We'll have this personal chat after your talk. So take the floor, please.
Thank you. And please tell me if my screen is visible and the slide can be seen.
Yeah, please. We can't see you, so see your slide.
Okay. Now it should be.
Yes, it's perfect now.
And here it goes in the presentation mode. So it's working fine?
Yes, please take it.
Okay. Perfect. So I'm going to talk about Square Kilometer Array, and it's an awkward name for a telescope, you would think, right? What is it? What is kilometer and what is array in this? And Square Kilometer here actually refers to the collecting area or the size of the telescope which will be collecting photons, the light that is coming from the space, and that's what gives it the name Square Kilometer. And array gives you an idea that it is not going to be just one element in the telescope, it's going to be a large number of elements that will add up to make this telescope. And that's what explains the name Square Kilometer Array. And this will be the world's largest radio telescope. And it is so large and it is so complex that it cannot be built by any single country or a small community. It requires all the intelligence and resources of all the astronomy community across the world. And that's what is happening with almost all the astronomy projects that are coming up, and no different for this radio telescope as well. So it is being built by a consortium of various research institutes across the world. And it will be built in two places. One will be in Australia and another will be in South Africa. And towards the end of my talk, I will explain why it is going to be like this. But the important point to keep in mind right now is that all the astronomers across the world, radio astronomers especially, are part of this project, and especially India is part of this consortium. So we are not only participating in building this telescope, but our community will also be involved in doing cutting edge astronomy with this telescope as well. But before going into like more details of square kilometer array, let us try to understand what radio astronomy is specifically, right? As you have been attending various talks since morning, and perhaps before that also, you would know that astronomy is just a study of emission that comes from various celestial objects in the sky, right? It could be sun, stars, galaxies, could be cold gas clouds in galaxies where stars will form in future, or it could be something like a cosmic microwave background radiation, which you may have heard about. It's the first light on the universe that we can see, actually, right? That very early stages of the universe. So all these things can be studied, and that's what is astronomy. And the idea is that we collect light from them. And when we talk about radio waves or radio astronomy is then referring to a particular aspect of it, which is that we are trying to study these objects at radio wavelengths. And why do we do it at radio wavelengths? The important point is that when we look at certain objects in the sky, the radiation that is coming out from them is due to a certain physical process that is going on in that object. And the radiation that comes at different wavelengths or different frequencies contains different information. It is very similar to taking an X-ray of a human body or taking a photograph through a simple camera, right? It shows different aspects of the human body, and by putting it together, we can then understand what a human body is composed of. And likewise, when we do astronomy, we try to collect as much information as is available at different wavelengths and our frequencies, and that tells us that what is actually going on in that. That if for example, if I go to this picture of our Milky Way galaxy, these different panels in this figure are showing you the image of our galaxy at different frequencies. At the top panel, you can see that it is at 408 megahertz, which is very low frequency. It is at radio wavelengths. You can see that you can see some bright regions, and then it does look like a disk. But when you move to the next panel, which is actually not looking at a particular a broad range of frequency, but it is looking at atomic hydrogen spectral line, which comes at 21 centimeter or 1420 megahertz. And you can see that it looks a little different. Actually, what this panel is showing is that the gas or atomic hydrogen, which is there in the galaxy, is actually distributed along the plane. Most of it is in the plane of the galaxy. And then you can move to the further panels as we go down the screen. You can see that there is infrared, which is showing us older stars. If we can go to say ultraviolet, close to, we are seeing younger stars in the galaxy. And then if we look at the optical panel, that's something which we are very much familiar with, because that's something which we have seen through even smaller telescopes, or even with the naked eye when we go for treks, for example, in mountains where the sky is very dark and very clear. You can see that we not only see these bright spots, but there are also very dark patches also. And straight away you can ask that what these dark patches probably mean that there is nothing there in the galaxy there, right? But if you look at the panels above, you can see that no, hey, at other wavelengths I can actually see that there are indeed stars in that region. So there must be something happening at optical wavelength that is preventing me to see what is in these regions. And that's pretty much the correct conclusion. What's happening that there are these regions in the galaxy which are very much rich in dust, and that's where a lot of star formation is also taking place. And since there's a lot of dust, you would know from phenomena of Rayleigh scattering, for example, that when there's dust, then the shorter wavelengths or higher frequency will be scattered more, right? Which means that the light from at those frequencies or wavelengths will not reach me. And that's what is happening here. So one of the advantages of going to longer wavelengths like radio frequencies is that we do not see this kind of scattering or extinction. And then it provides a deeper view of a galaxy to us. And then also it at the same time gives us an opportunity to understand different physical processes that are going on in the galaxy, right? So that's the idea, that we want to study objects at different frequencies or wavelengths, and radio astronomy, for the same reasons, acquire a very unique place in astronomy. So now let's get a little bit more specific about how do we actually do radio astronomy. So now this panel or this graph here is showing you the transparency of our atmosphere, which means that, like, if let's say some radiation is coming from the sky, then how well it can pass through the atmosphere. Because if it does not pass through the atmosphere, then I cannot receive that, collect that radiation from ground. But if you look at this region from 1 millimeter to 10 meters here, where there's this big gap in this graph, that's where the radio astronomy is done. And specifically, if you look at it, extends from like about 0.3 millimeters and goes up to 30 meters, right? And on either side of it, you can see that the transparency of atmosphere is very low. And on the high end side, what is happening, which is around 10 meters, is that ionosphere, that's the plasma layer in our atmosphere, is actually blocking all the radiation. So radiation cannot come. And if you go to the other end of it, then there is things like water vapor in our atmosphere, which will absorb that radiation, and that will also not come here, right? So if you want to do astronomy at any of these regions where you can see that the radiation is completely blocked, we need to go to space, right? That's why in the graph at the top, you are seeing that if you want to do X-ray astronomy or ultraviolet astronomy, you have to go to space and build telescopes like Hubble Space Telescope or Chandra Telescope. But then there's another small window here, which you can see close to 100 nanometers to 1 micron, where you can see that there are these optical telescopes which can be built on ground, and we can do astronomy, right? So optical astronomy and then radio astronomy here, you can see that these are the two places where we can do astronomy from ground, right? So there are some very special things about radio astronomy or the radio window itself. One is that it is extensively used by mankind. We are very much familiar with it. Our microwave ovens, mobile phones, Wi-Fi, FM radio, all these things actually are operating at radio wavelengths, okay? And this is just explaining mathematically here that how we can estimate a frequency beyond which the radiation will be blocked by the ionosphere. I'm not going to go into the details of this, but if anyone would like to read more about in detail, you can look into concepts related to plasma frequency. And it's something very important for our communication on ground as well. Okay, this is something which we have discussed itself, that radio astronomy acquires a unique place in the study of celestial objects. So let's now talk about historically, like what is it that we are trying to understand when we are looking at celestial objects. We are, of course, collecting photons or light at different frequencies. That's what we want to do here. And one concept which you must be very familiar with is the idea of black body, right? If an object is a black body, then this is how its radiation will depend on as a function of, or vary as a function of, frequency or wavelength. You can see a curve like this, and purely the placement of this curve will depend on the temperature of the body. You can see if the temperature is larger, the peak will be at a higher frequency. And this is how we understand sun and other objects which we can approximate to be a black body. So just keep this idea in mind, because I'm going to tell you some simple, interesting things about radio astronomy based on this. Okay. So now, how was radio astronomy started in the beginning? It was not a very planned activity. It actually started by chance, and that happened in a very early 20th century. And an engineer named Carl Jansky, he was working at Bell Labs, and he was actually investigating a certain noise which was coming in transatlantic communication, that is between USA and Europe. You can think like that. And there is this special telephone line through which people want to talk, and there's a lot of noise coming into that. So he started investigating. His company gave him this charge, okay, you go and investigate what is going on here. That's what your job is. And he started looking at it, and he found that there is a certain signal which comes and follows certain periodicity as the time in the day progresses, and it's coming from a certain particular spot in the sky. And that's what he found. And later, as he investigated more, he found that it's actually coming from a certain region of our galaxy corresponding to the galactic center here. That's how he was able to pinpoint that that's where the radio signal is coming from. So this was pretty much the first discovery of radio signal coming from a celestial object in the sky. Prior to that, people did not really actually had detected anything from space at radio wavelengths. And the reason was because at that time, the technology was not advanced enough, because the signal that is coming from space is very, very weak. That was one thing. And second thing is that a lot of people were trying to detect radio waves from space, but they were trying to do it at very low frequencies or very long wavelengths, like maybe 1 meter or even not 1 meter, I meant like 50 meters or much longer than that. So these are the wavelengths which are actually blocked by the ionosphere. And at that time, understanding of ionosphere was also not very well developed. So because of these reasons, people thought that there's not much to be detected at radio wavelengths. But when this thing happened, then this triggered a lot of new ideas among astronomers across the world. Hey, there is a lot of interesting stuff which can be done at radio wavelengths. And this was indeed the case. And the next person who did some very important pioneering work was Grothe Rieber. And he also wanted to actually continue with radio astronomy, which is exactly where Jansky left. But he was not allowed to do so because there was no funding available at that time to do astronomy. Just like we have radio astronomy research institutes today, it was not at that time, right? These are the first people who are trying to detect something from space. So nobody wanted to put money into that. So what Grothe Rieber did, that he took up a job somewhere, but he built this telescope which you're seeing here on the screen in his backyard. And he started doing radio astronomy here. And he started making maps of galaxies. But initially, when he pointed his telescope and when he was starting to doing his experiment, he was trying to do them at very high frequency, like 3 gigahertz or 5 gigahertz. Because Jansky, if I tell you, he was doing his experiments at about 20 megahertz, right? So at that time, he thought that the objects which are there in the sky are like black body. So if I go to higher frequency, then I will be able to detect much stronger signals. That's what he thought, right? And that's the kind of planning or understanding of physics goes into doing astronomy or actually planning any experiment. So because you collect all the existing information that is there and all the physics that is known about the kind of objects which you may be looking at, and you put these together and you plan your experiment, right? And that's what Grothe Rieber did. And he detected nothing. So he thought, okay, but he did not give up. So he moved down. He started going to the lower frequencies. And then at some point when he came down to 1 gigahertz and lower, he started detecting things which Jansky was discovering, right? So this led to this idea that actually these objects which he was detecting in the sky, and prior to that Jansky detected, they're actually giving radiation due to a different physical process. So they're not black body. And black body objects are also called thermal, as I was saying that, like, you know, that the emission is just coming from the virtue of the temperature of the body, right? And that's not the case here. Actually, it's the graph, if you plot, of a non-thermal body will go completely opposite to it, right? And at the same time, the physics was also developed to understand where this emission may be coming from. It actually comes from electrons which are there in these objects, and they are at relativistic speeds going around the magnetic fields which are there, right? So, and then the process is called synchrotron emission. And that's something which is very ubiquitous in all the celestial objects. And that's the kind of thing which we detect at radio astronomy. So here you can see an idea of like how both the physics and experiments actually move hand in hand, right? So then with this, there was like a big boom in astronomy, radio astronomy, and the first quasars were discovered. These are the most powerful objects in the universe. They were discovered. Then you know that hydrogen is the most abundant element in the universe, and to study it is really crucial, because from this we can then understand how this reservoir of hydrogen goes into galaxies, gets converted into stars. So it's very important to understand galaxy evolution. Then we need to understand how the hydrogen gas is distributed all around, right? So that's something very crucial too. So this line of 21 centimeter, which comes from the fact that the ground state of hydrogen atom actually has got different energy, different frequency, depending on whether the electron and proton spin are parallel or anti-parallel, right? So this line was theoretically predicted and was detected in 50s. And that's something which has led to a lot of what we know about galaxies in the universe. Then microwave background radiation was detected in 64. You know that Nobel Prize has been given to it. It's something very fundamental about our understanding of universe. Then the discovery of pulsars happened in 60s. That's by Jocelyn Bell Burnell and Anthony Hewish, again got a Nobel Prize. And then pulsars, as you know, that not only that they are very interesting objects in their own right, but they also allow us to test Einstein's general theory of relativity in some very interesting regimes. And that particular, some initial studies on that has also been given Nobel Prize, right? So radio astronomy has led to some very key discoveries and made some very important contributions to our understanding of the universe. So next step is now to actually build the largest radio telescope that one has. And the idea is to build largest telescope is that you should be able to, you want to detect objects which are very faint and very far off, right? You want to now go and see the earlier stages of the universe. That's the idea. So this is the largest steerable dish that we have currently. It's a 100-meter telescope called Greenback telescope, and it is there in USA, right? And there's nothing larger and more steerable than this because it's very difficult to make these dishes bigger than this. They are very heavy, right? So the basic principle of radio astronomy to build very large telescopes is based on what is called as radio interferometry, where instead of making a very large dish, what is done that we actually gather or make smaller dishes. Like here you can see in this picture where one sees 30 dishes of GMRT or Giant Meter Radio Telescope near Pune. And these dishes are then actually, we take signal from them, we combine them in pair, and when we do something called a Fourier transform of it, it actually gives an image of the intensity distribution in the sky, or like how the sky is looking where the dishes are pointing. That's how radio astronomy is done. And this technique is so fundamental that it itself also got a Nobel Prize in 1974. And so that has been in use since then. And SK is going to be built on this. So this is how it will be. And it will be actually split into two components. Something which is at higher frequencies and will be having dishes like this will be built in South Africa, and another component of it which will be operating at very long wavelengths that will be built in Australia, because that will be using a different technology. So it's possible to build them as slightly different components at different places. And this is the biggest telescope which is going to happen in next 3 years' time. That's what will happen. And so this is just a view of how the site will look like. And this, you can see like these large number of dishes, how they will be placed in South Africa. And you can see that there's nothing here. It's being built in desert. That's why people have gone to places like South Africa and Australia. But as I was telling you that radio astronomy, we also use a lot of our instruments at radio wavelengths, like our mobile phones, microwave ovens, and all those things will affect the faint signal that is coming from the sky. So we want to go to places where we don't have any of this disturbance. And this is the kind of telescope that will come up in Australia. You can see like it's a different kind of a detector that is being used there, right? They're called dipoles. They will collect radiation from the sky and will allow us to make maps of how sky looks at that low frequency, right? So these are the basic goals of SK, and that's where like, it's going to touch every aspect of astronomy, starting from galaxy evolution and cosmology, testing Einstein's theory of relativity, and even trying to understand like if life exists at certain other parts of the universe, and trying to understand like are we really alone, and we do have some neighbors as well. So all these things are going to be done with SK, and we are all getting ready for that. So I'm going to stop here, Samir. If there are some questions, we can go through them.
Yes, definitely. And what a lovely presentation about the biggest telescope that is coming up, and over 2 continents. That is amazing. It's mind-blowing, basically. Thank you for also sharing the videos, which shows, the pictures speak much louder than words. So it's lovely that you shared it at the end. I can see that many people here in the audience are interested and excited by this project coming up. Yes, there are questions. We're just collating them. You said at the end that yes, these have to be made far away from radio sources, and I just remembered an anecdote that some radio astronomers from a radio telescope were noticing that they were getting some strong signals, some particular signals, and they were unable to explain them. And so after a while, they studied the pattern, and it seemed it was coming very close to lunchtime because people were using some microwave somewhere.
Yes.
Getting detected.
Oh, yes. So in fact, some of the very interesting discoveries, people think of them. So pulsars, when pulsars was discovered for the first time, people thought actually that it's a signal coming from extraterrestrial intelligence, like it's a green man kind of a thing, right? And when things like fast radio bursts were discovered for the first time, it took astronomers a very long time to actually confirm that these are actually coming from space and not, people thought like they could be coming from microwave or some radio frequency interference, because some of these signals, when they come, they are very strong and it's and peculiar in nature, and it's difficult to then immediately understand that where they could be coming from, because it's not just enough to detect, right? Something we have to also explain where is it coming from and the physics behind it. So in like in any branch of science, in astronomy too, the detecting or finding something is only half the job. It's completed only when we can also explain that what it is about.
That's true. That's true. Yeah. And thanks for doing this job, and thanks to all the radio astronomers who are doing this job, and such great aims for the science that can happen with this science. Doing science is something people don't understand, but doing science means basically researching something. It's a general word to say science here. Wow, so many, from right from life elsewhere to understanding the earliest times and places in the universe. Lovely. Okay, so the questions are coming, and of course, a very basic question. I think you have answered this, but why is it necessary to study the universe in radio wavelengths? Just
Yes, so I can go back to my slide, in which I was showing that galaxy looks so different at different wavelengths. Right? It is just our own galaxy, Milky Way, right? And if you look at the fourth panel from the bottom, which says optical, and this is what it will look like if you just look at it only in optical. And you can see that there are these dark patches there, and some parts of the galaxies are blocked because like there's a lot of dust in the galaxy. But just by looking at this, I cannot tell that. First thing, I cannot tell that what is happening there. So if I go to other wavelengths where this blockage is not there, then I will be able to see those parts of the galaxy. That's one thing. And radio astronomy, since it's based on longer wavelengths, allows me to do that. And the second thing is that at radio astronomy, I can, for example, look at neutral hydrogen, which is, you can see the second panel from the top. And so this is the main reservoir from which the stars are forming, right? So if you give me an optical or an ultraviolet map, where I can see stars forming in the galaxy, and if I go to the second panel from at the top where I can see how much hydrogen is there in the galaxy, then I can tell you that how long this galaxy, for example, can continue to form stars, because stars have to form from this neutral hydrogen. That's the basic reservoir that is available in the galaxy. So just by looking at this one map, I cannot actually build a complete picture or get to what all is going on in the galaxy. But if you put these 2 or 3 different panels together, I can tell you that this is where this galaxy came from, whether this galaxy is going through a merger, it is interacting with any other galaxy, how long it can continue to form stars, how many stars are young, how many stars are old. And if you do it for many galaxies, then we can actually tell that how the different galaxies were evolving at different stages of the universe. And this is true not just for galaxies, we can do it for any other celestial objects too. And that's why it is important to study at different wavelengths. And radio has its own place because it allows us to study some physical processes that we cannot study at other wavelengths.
Okay. Yeah,
it's like if I want to take a bone structure, if I want to study your bone structure, I have to take an X-ray. There's no other way I cannot. If you have got an injury in your hand or leg, and I suspect that it's due to a fracture or something, I'll have to actually take an X-ray, doctor. Otherwise, you cannot know what is going on there.
So complete diagnosis.
Exactly.
Astrophysical object. Yeah. Possible with all kinds of studies, including radio. That's great. And multi-wavelength astronomy is very exciting, it seems. Definitely. So we have some questions about for new comers in this field who want to know, like, can amateur astronomers also build a radio telescope? Is one question.
Yes, actually, and IUCAA has some programs through which they help people to build small detectors or small dishes that like for example, dishes that are used or used to be used at some point for our cable TV reception, right? So like even older people would know that, like even to receive standard normal Doordarshan for 2 hours in the evening, you had to have antennas at the roof. So IUCAA has small programs. Time to time, there are schools which are conducted to teach interested students to build some small telescopes through which they can study things like signal from sun, from our own galaxy. These are the strongest signals, so that's why a small instrument can detect them. So yes, there are programs, and it's very much possible. And I told you about Brothe River, who built it in his backyard, the first radio telescope. So it's possible.
Yes, definitely. And I'll request people here to go to our poster exhibition, which is at the website, which is also being flashed once in a while in this thing. So there are a poster exhibition in which various sub branches of astronomy are being covered, and you can go there and quickly find out the work with radio astronomy, other work with radio astronomy done in IUCAA. And we have something called the Radio Physics Lab in IUCAA, which is a very active group. And if you look it up on our website, you'll be able to contact them, and they should be able to help you out with your own efforts in making a radio telescope at home. So all the best for that. And if there's any any roadblock, any hurdle, let us know about that. So and good that you have this initiative. Also, I think there are people who would like to know how they themselves can get access to this data from professional telescopes, and could they use it to make some images, or could they use it to contribute to science?
Yes, all the data that is collected in different telescopes becomes public after 1 year or 2 years of observations, and it can be downloaded by anyone to their own desktop or computers. And many times there are also ready-made softwares that are available, which one can use to make images. And of course, like one has to understand like which data to collect and which what tunings to use in the software to make the and all that is interesting to learn. But yes, anyone who has an interest and wants to put some effort can actually get data from any of the telescopes across the world, right? You can start with GMRT, which is like close to Pune. It has an archive where all the data that it collects becomes public. And likewise, you can go to websites of like Very Large Array, which is based in USA, or Greenback Telescope in USA, and the Meerkat Telescope in South Africa, for example, which is the SKA precursor. That telescope's data is also becoming public gradually. So yeah, you depending on what you want to do, you can actually get the data and do it yourself. You don't really have to be based even at an institute.
Okay, that's great. Yeah, so citizen science is possible, and we should look out for these individual telescopes who are providing access to their data. In fact, Neeraj, you work with the GMRT here, right? So
yes.
How's your experience, and how did you feel when you first used it?
Oh wow, that was so when I was a master's student, I came to GMRT to do a short project, and at that time I did not know anything about astronomy. But what I was interested in was making images, and those images could actually come from just photography, could be painting. So I was just interested in anything which is visually and aesthetically nice. And I thought like, then why not try to look at something which is there in the sky too? And that's what pulled me towards astronomy. And I thought, and at that time I knew that GMRT is and it still is one of the world's largest radio telescopes. So like, why not use the best camera if you can? Right. So I came there to do a project, and the first time when I did actually observed with that, and that was a very, I could say, an eye-opening experience at different levels, because a telescope, during our post-graduation, graduation, we learned so much of experimentation, engineering, and basic physics and mathematics, even concepts like Fourier transform, for example, right, and some electronics. But we never put them into into practice at a level where it actually, we think that, oh wow, that was amazing, right? So a radio telescope actually collects signal, combines them in pair electronically, and then it does a Fourier transform of it to make an image. And the whole entire operation is very similar to the lens in our eye. That's what is going on. So this basic idea of actually, right, that is something which happens in nature so easily at optical wavelengths, but engineers and scientists, because of they're so clever, they can actually put together this whole system together, which can actually do the whole thing for you at radio wavelengths, where there does not exist a lens in the nature, right? If you go out and mining, you will not find the material from which you can make a lens that will work at radio astronomy, but you can actually electronically and with some mathematical understanding do that, right? So that was the thing which actually pulled me into radio astronomy, and still that's what I find is most fascinating.
Wow, that's truly amazing, and thanks for making us realize that fact that yes, there are no lenses.
Yeah. So it's not just talk; it's actual work, right? That's what it becomes in astronomy.
That's right. Perfectly put, and I think that should be very inspiring for the students to come into this field of astronomy and radio astronomy, if possible, with all these great tools being already available and coming up. So that's a really good advice. Now, I think we're coming to some of the more complex questions after the simpler ones. One of the questions is that I'll combine actually two questions. One of them is simpler. Does the sun emit radio waves? And what is this H1 line that you've been mentioning? And is it related to the sun?
Okay. So sun, of course, emits at radio waves, and it's actually very strong at radio waves. And especially at you go to more wavelengths. But what happens that if you take sun and put it at, let's say, 1 parsec, right, which is not very large distance in astronomy, right? It may sound like, hey, why I'm putting it so far, I'm cheating you. No, actually, I'm being generous by putting it at 1 parsec in astronomy. The signal that you would expect is like of the order of microjanskis. Which is, to put it in perspective, it is so faint that even if you take the best telescope in the world today, it would actually, you will have to observe for days and weeks to detect that signal. So what this is telling you is that, yes, the kind of object we have, sun, as a star, it actually emits at radio waves, but at radio waves, its signal is weak. And that you can understand because you can see that this curve, as I go towards longer wavelengths, it is actually falling, and sun and stars are black body. So the signal that we expect from them is weak. But then there are other objects in the sky which are much, much more powerful than sun at that distance. When we have to always think of distance as well when we are talking about strong and weak. So yes, sun and stars do also emit radio waves, but it's weak. That's the answer. And now talking about the H1 line. Mm-hmm. So it's using the notation of chemistry where H corresponds to hydrogen element. And this is Roman 1, actually. A lot of people call it high also when they are new to the field. But it is actually H1, which means that it is neutral. Right, the electron which is there is also bound. As for example, like if I can take carbon, for example, it can have C1, C2, C3, C4, which means that with every Roman number being added, I'm taking out 1 electron from it, right? So H1 means it has neutral hydrogen, and the 21 centimeter line is actually corresponds to the wavelength of the line, which is very specific to this atom, and it comes from the fact that the ground state of the atom, right, it gets split in the presence of a magnetic field. It has different energies, basically. This ground state is split. You can think of it like this. And what are these two states corresponding to? In one state, electron and proton spins are parallel to each other. And in another one, they are anti-parallel to each other, right? So now you know that instead of one state, it is now 2 states. So this means that one can make a transition from one state to the other, right? And depending on whether it is going from lower state to higher and vice versa, there will be a photon emitted or photon that will be absorbed, right? So this transition is happening at 21 centimeter, which comes in radio wavelength. The special thing about this is that it's a fantastic tracer of neutral hydrogen gas. And neutral hydrogen gas is so important because it's the most abundant element in the universe. So it's the basic fuel for everything that is going on, right? If you want to understand galaxies, if you want to understand space between galaxies, how the gas is distributed there, this can be a very powerful tool, this particular line, to study neutral hydrogen at different parts of the universe. That's why there is this is given so much importance.
Right. So one of the most prominent lines in the radio studies. Great. So I hope that answers the question. It was really a good question and about one of the most important lines, as you said.
Yes.
Right. We have another nice question from Piyush, who wants to ask that, is it possible to detect sub-radio wavelengths? So I'm not sure what that means, but it probably means things beyond the largest radio wavelengths of the lowest.
Oh yes, of course. Like, so you can see that. So I was talking about this radio window here. You can look at it, this graph between 1 millimeter to, let's say, 30 meters, right? And so if you want to go beyond 30 meters, ionosphere, the plasma layer in our atmosphere, is blocking the radiation. So from ground, we cannot detect it, right? Because anything which is coming from the top is getting sort of bouncing back, right? It is not coming in. So what we need to do is to go into space. So radio astronomers, one of the things they want to do over the next couple of decades is to build a telescope on Moon, radio telescope on Moon, because then we can look at radiation which is coming in these frequencies. Not talking about a lower edge of it, when we come to this part, it's the water vapors and other molecules which are there in the atmosphere start absorbing it, right? So then again, it cannot come. It is like sort of getting absorbed in the atmosphere and it will not reach my telescope here. So what I need to do is to go to places on the planet which are very dry. For example, people go to very dry deserts of Chile, like Atacama Desert, where it has not rained, I guess, for last 150 years or something. It has not rained there, right? It is such a dry place and it is at an altitude of about 500,000 meters, right? So it's at a high altitude also. So it's a very dry place, and that's where we can do a little bit more astronomy at these. But otherwise, if we want to go further, shorter wavelengths, then we have to again go to space, and that's called infrared astronomy. Then we have telescopes like Herschel, for example, and we have to do that astronomy again from space. But again, like then there comes a small window of optical wavelengths you can see right here, where we can again do astronomy from ground.
Cool. Wow, so that's another revelation that you have to really find these special places on the Earth to do astronomy, and maybe even in space or on the Moon.
Yes.
Lovely. Great. So this has been a great interaction. We are through with the questions. So let us thank Neeraj for being here and sharing his work with us. Thank you so much.
Thank you.
And now we'll move on to our next speaker, who will talk about another proud project that India is involved in, which is, I think Neeraj is also involved in that as well, which is the 30-meter telescope project. So we will be having Professor Ram Prakash coming in to talk about the 30-meter telescope. As I have described to you, it's a giant eye. It's going to be built on the Earth, and such a audacious project is not yet in space like the Hubble Space Telescope, which is a tiny telescope compared to the 30-meter telescope, although very useful. It's 2-meter class telescope. So now we're talking about 30-meter class. And here is Professor Ram Prakash with us at a scenic location today.
Thanks to Zoom.
Thanks to Zoom.
Because we cannot travel. I would have liked to be there, but I can't be because of Corona.
Welcome to the event, and we're looking forward to your talk. We'll have a little personal interaction at the end of the talk. But,
sure, no problem.
Please take the floor, and we're eager to hear.
Okay, there is no gap between the talks. It's a continuous. I can start straight away.
People are at their home, so they can have tea and lunch.
No problem. Great. Okay, so let me start my sharing my screen, and then I will take it from there.
Thank you.
So let me start the screen sharing. Can you see my screen?
Excellent. We can see it. Thank you.
Okay. Good afternoon, everyone. It's just closing on lunchtime. So I hope you will all be listening to this talk and eating your lunch at the same time, which is both important. So what I'm going to talk to you about today is the 30-meter telescope project. It's an international observatory in which India is a partner along with institutions in the US, in Canada, in China, and Japan. So it's a multinational program to build an extremely large telescope, which would allow us to see deeper and farther and fainter into the sky at unprecedented levels. And so let me try to explain, to start with, why we need to make such a large telescopes, and then understand what 30-meter telescope is all about, and then in the end try to understand what kind of discoveries we expect to make with such a facility. So let me start with the first question. What do telescopes do for an astronomer? Why do astronomers build telescopes? So if you ask that question naively, one would ask, if you look through a telescope at a distant object, the object appears to be closer. And that's a function of the telescope. So the telescope, if you look through a telescope at a distant object, you appear objects which are closer. And to understand this in the context of astronomy, we need to understand a little bit more about what you mean by bringing an object closer. And that has two aspects. One is, when an object comes closer, you collect more light from it, and you start seeing more details. For example, if there is a candle which is very far away, you may be not able to see it, but if you look at it through a telescope, you collect more light from it and your eye starts seeing it. And similarly, if a person is standing very far away, you may not know who it is, but you look through a telescope, but then you start seeing more details of the person's features on the face, etc., and then you know who it is. So the telescope, by bringing objects closer, allow you to collect more light so that you can see fainter objects, and also allow you to see fine details so that you can study more about that particular object you are looking at. And there are two properties of the telescope which allows this ability to make the objects brighter and allow you to see finer details. Those are the diameter and the focal length of the telescope. So if you think of a telescope as a large piece of lens, or as in the previous speaker said, a dish antenna, the diameter of that lens or the antenna is what decides how much brighter an object becomes. And the focal length of the telescope is what decides how much fine details you will be able to see. So Galileo was the first person to use a telescope to actually look at the sky and try to understand what is going on in the celestial sphere. Telescopes existed before that, but Galileo was on record. He was the first person to look at the sky and try to make some systematic studies. And Galileo's telescope had a focal length of about 40 millimeter. Diameter of about 40 millimeter, less than 2 inches maybe. But the largest existing telescope today has a diameter of 10 meters. I'm talking about optical telescopes now. Of course, there are radio telescopes which are much larger. Those who attended the previous talk would have heard of very large radio telescopes of much larger diameter. But let me talk to you about optical telescopes, the kind of telescopes which collect light, the kind of light which kind of human beings can see, visible light, and nearby wavelengths. So among them, Keck is the largest telescope and it has a diameter of 10 meters. Similarly, Galileo's telescope had a focal length of less than half a meter, but modern large telescopes like the Keck has a focal length of 150 meters. So you can see that from Galilean times, in the ability to, we have come a lot forward in both the ability to see fainter objects and to see finer details. In both aspects, we have come a long way forward. Now, when you start looking at astronomical distances, because telescopes allow you to bring objects closer, let us also understand how far are these distances, how far are objects compared to celestial, compared to distances on the ground, on Earth, etc. These are enormous distances away. So astronomers use special units to measure these distances, not meters or not kilometers. They have to use much larger units of measurement to denote these distances in celestial, to study celestial phenomena. And one such unit is an astronomical unit. Many of you may know about it. That is the mean Earth-Sun distance. So as Earth goes around the Sun in an orbit, the radius of the Earth orbit around the Sun, the mean radius, it's a slightly elliptical orbit. So the mean orbit is called one astronomical unit. We all know that light takes about 8 minutes to travel from Sun to Earth. So 8 times 60 is the number of seconds it takes. And 3 × 10⁸ is the velocity of the light as it travels through vacuum. So 1.5 times 10⁻11 meters is one astronomical unit. You can see that is a very, very, very large distance, an enormous distance. But even this unit may not be sufficient for astronomers to denote distances to faraway objects. So they use another unit called light year. And of course, many of you may know what a light year is. It is a distance traveled by light in 1 year. So there is about 3 × 10⁷ seconds in 1 year, and 3 × 10⁸ meters per second is the velocity of light. So 1 light year translates to about 10⁻XVI meters. So it's even larger than an astronomical unit, 10⁵ times larger than an astronomical unit, 1 lakh times larger. Even this unit, a light year, may not be enough for astronomers because we are talking about very, very large distances. So astronomers use another unit called a parsec. So let me try to explain what a parsec is. If I take a stick like this, and if I draw 2 lines, the red lines from the 2 edges of the stick, and the way that they converge at a faraway point. So these 2 lines obtain an angle at the point where they converge. Now, if I move the stick far away, the angle becomes smaller. So as you move the stick further and further away, the angle which it subtends at your eye is smaller. The angle between the red lines are larger than the one between the blue lines, and the angle between the black lines are even smaller. So as you move the stick farther and farther away, your angle at your eye becomes smaller and smaller. Now, if I take a stick, which is 1 astronomical unit in size, and then see how far away you have to go so that this angle is 1 arcsecond. So those of you who do not know what an arcsecond is, if you take 1 degree, which is a small angle, divide it into 60 individual units, you will get 61 arc minutes. And each arc minute, if you divide into further 60 equal units, you will get an arc second. So 1 arc second is like dividing 1 hour into minutes and seconds. You divide degrees into arc minutes and arc seconds. So arc second is a very, very tiny angle. And this stick is a very large stick. It's 1.5 10⁻11 meters in size. So you have to go very, very, very far to make this angle so tiny. And that distance is called 1 parsec. Now, if you calculate that, you will see that 1 parsec is about 3¼ times a light year. So 1 light year, 3¼ times a light year is 1 parsec. So let us use parsec as our standard unit for distance measurements. And then if I take a star which is very close to our sun, the nearest one is Proxima Centauri. The distance from the sun to the nearest star is about a parsec, 1.3 parsec roughly. So typical stellar distances within our galaxy, the distance between stars within our galaxy is of the order of a parsec or few parsec, etc. Stars are separated by one or a few parsecs apart. On the other hand, if I take the entire size of the Milky Way, our galaxy, it's about 20,000 kiloparsecs, 20,000 parsecs or 20 kiloparsecs. So compared to interstellar distances, the size of our Milky Way is 20,000 times larger. Milky Way is enormous compared to interstellar distances. Now, similarly, if I take the distance to the nearest galaxy to our galaxy, the Milky Way galaxy's nearest galaxy are two small dwarf galaxies called Magellanic Clouds. They are about 50, 60 kiloparsecs away. You can see that the size of the galaxy and nearby galaxies, etc., are 20,000, 50,000 times interstellar distances. So it's a huge factor. Now, if you take it to the next level, I look at the nearest galaxy, big galaxy to our galaxy, it is almost a megaparsec away, 1,000 times further than typical interstellar distances. So the galaxy to galaxy distance is a factor of 1,000 more. Now, if I look at the size of our visible universe as it stands today, it is about 4,000 megaparsecs or about 4 gigaparsecs, another factor of 1,000. So as you can see, in astronomy, we are talking about enormous distances, very, very, very large distances. Interstellar distances themselves are very large. No man has, or no human being has ever traveled from one star to the other, not even send a probe from our star to the nearest star. So it's just too far away. Even if you travel at the speed of light, it'll take 4 years to get from our star to the nearest star. So it's very far away. And then compared to those distances, our galaxy is enormous. Intergalactic distances are another factor of 1,000 larger, and the size of the universe is even another factor of 1,000. So enormous distances. So when you talk about these enormous distances, let us try to understand how a telescope helps in making an object appear closer. To understand that, I put a star in the sky here. And this star, as you can imagine, is enormously far away compared to any distances you can think on the Earth. Now, the light from the star is radiating away in all directions. And then if you, that light is propagating away from the star as time progresses. As you can see from the light, the star, the light is going away and it's just expanding away from the star as time goes away. And the important thing to notice here is, if I sit very far away from that star, extremely far away, as we had seen in the previous explanation, the distances are very, very large. So if you sit very far away from the star, this sphere of expanding light becomes so large that it is no more appearing to be a sphere. It is almost like a plane surface. The curvature of the sphere is almost become very negligible. It's almost ignorable. It becomes almost a plane surface. So the farther you go away from the star, the more planar the surface becomes, the way the light arrives at you. So instead of light radiating away from the star, it appears as if the rays of light are arriving at you parallelly. Instead of diverging like this, they are appearing parallelly to you. Now, in this case, if you sit on the Earth and use a telescope to look at this star, if the telescope has a large diameter, it will collect light from more area of this surface and the star will appear brighter. And if the telescope is collecting light from a small part of this surface, the star would appear fainter. So depending on how large the diameter of the collecting aperture of the telescope, like the lens or the mirror which forms the telescope, you collect more or less light from that star, and therefore the star appears brighter or fainter to you. And that's how a telescope makes an object brighter. Even a single point source in the sky like a star appear to brighter or fainter because of this phenomenon. Now, how does this telescope allow you to see fine details? To understand that, I put another star here, a red star right next to the black star. If the telescope is able to see the light from these two stars as separate, you will see two stars. If the telescope is not able to see the light coming from these two stars separately, you will see one blob of light and you will not know there are two stars there. Now, how does the light from the red star arrive at the telescope? The way it arrives at the telescope is at an angle compared to the light arriving from the first star. The black star light arriving at you along the black ray directions, while the light from the red star is arriving at you at an angle compared to that. Now, if the telescope is able to distinguish the angle of arrival between these two rays, the telescope will be able to see these as two spots. If the telescope is not able to distinguish this angle, if it thinks that the light is all coming at the same direction, it will not see them as two stars and will appear as one blob of light. Now, the ability of the telescope to distinguish this angle of arrival of these rays depends on the focal length of the telescope. And that is how the focal length allows you to see finer details, while the diameter of the telescope is what allows you to make the star appear brighter. So let me try to put this a little bit more in terms of a ray diagram, which many of us would have learned in our 10th standard, 12th standard, etc. Here I'm representing my telescope with a lens, which is shown in green here. So that lens has a focal length of f, as I marked here, and a diameter of d. So light from that black star from the previous slide is arriving as parallel rays and falling on the lens. And of course, the lens will converge that to a point at its focal plane at a distance of f from the lens. So at that point, you get an image of the star where the rays converge. Now, if I take the light coming from the red star, they are arriving on the telescope at an angle, small angle, and those rays would converge at a different point at the focal plane of the telescope. And at that point, the image of the second star will be formed. Now, if the separation between these two are sufficient to see them as two spots, you will see two stars. But if this separation is so small that it becomes one blob of light here, you will not see them as two stars. Clearly, if I look at this, if I mark this angular separation between the two stars as theta, which is this angle, same angle, because these lines are just traveling straight through the lens at the center of the lens. So this angle is theta, which means this angle is theta. This separation h is given by f theta. For small theta, it is given by f theta. So therefore, you can write down the equation that f theta is equal to h, or reorganizing it, you can see that the angular separation in the sky theta is given by the linear separation h divided by the focal length of the telescopes. Therefore, it is just the focal length of the telescope which defines what this separation is, and therefore whether you will be able to see fine details on the sky. So if two stars are separated by an angle theta in the sky, the images of those two stars will be separated by h separation, which is given by f theta at the telescope focal plane. And if this separation is sufficient, you see them as two stars or 2 points on a galaxy. If the separation on the focal plane is not sufficient, you see that one blob of light, and therefore you lose the details. And that is how the focal length of the telescope allows you to see fine details. Of course, the diameter is what makes sure decides how much light you collect from the star. Now that we understand that we can collect light from the star using a telescope and make objects brighter, what is the faintest object you can see on the sky? Can we see objects fainter than the sky itself? For example, if you go out in the daytime and look at the sky, you don't see any stars. This is because the sky is so bright, emitting so much light coming from the sky, that the stars are all fainter and you don't see them. Now, is it possible at all using a telescope to see objects which are fainter than the sky? Now, to understand that, let me do an illustration here. So this patch, the dark patch, is a dark part of the sky in which there's a star. You can see the star clearly. It is very bright and you can see the star clearly. But if I make the star fainter and fainter, it will slowly become impossible to see. So if at the next level, I'm just making the star a little more fainter, it is impossible to see it because the star is still there, but you don't see it because it is just fainter than the light emitted by the adjoining sky. Now, if I make the sky darker, you can see that the star is still there. It comes back. So when the sky is darker, you see the star again. It is still there. So the star is still there, but because the sky is bright, you cannot see. So the question is it possible to see objects which are fainter than the sky? Now, to do that, one possibility is you just look at this direction of the sky. From there, the total light coming will be the light from the star as well as the sky. Let us imagine that the sky is producing 100 units of light or 100 photons, and the star itself is only producing 1 photon. So the star is 100 times fainter than the sky. Now, in that case, if you look toward this direction, you should get 101 photons. And if you look at this direction, which is very close by that star, you will get 100 photons because sky is only emitting 100 photons. So this part direction, you get more number of photons or more amount of light. And if you subtract the light of this region from this region, the direction toward the star versus the blank sky, you should be able to see the star. But the problem with this approach is every time you make a measurement of the light coming from the sky, there is always an inherent error or noise or measurement uncertainty. This measurement uncertainty will define whether you will be able to see a faint star in this direction compared to the amount of skylight coming from this direction. And the uncertainty in measurement is defined by this, that if you collect n photons or n units of light from any direction in the sky, total number of units of light you collected is n, there is an inherent uncertainty of root n. That is, if you collect 100 photons from a part of the sky, you can only say that, okay, from that part of the sky, I get 100 units of light plus or minus 10 units. 10 is the root of 100. So 100 plus or minus 10 units. This is inherent in the process of measuring light. This has nothing to do with your telescope, nothing to do with your detector, or nothing to do with how you are doing the measurement. Any measurement of photons or any counting of photons using a detector or a telescope involves this uncertainty. That is how photons are made. It is inherent in the nature of photons. So if you collect 100 photons, you can only say that it is correct to 100 plus or minus 10. So going back to the direction of the star, if the total light coming from there is 100 on an average from the sky and 1 from the star, you are getting only 101 photons. But that measurement is uncertain to root of 101, which means roughly 10. So you have made a measurement only 101 plus or minus root 10, roughly. You don't know whether it is compared to this part also, which is also unknown, 100 plus minus 10. You don't know from there is one count extra coming from there or not, because your measurement is uncertain, or the noise in your measurement is at the level of 10. You don't know whether there is a star there or not. And that is the problem. So even if you try to subtract the sky off, the sky measurement being uncertain to root of the number of photons you collected, you always have an uncertainty, and therefore you will not be able to see that star there. Now, is this a limitation? Does that mean that you cannot see a star fainter than the sky? No. So let me try to explain it with a table here. The first column of the table shows the number of photons you collect from the star. The second column of this table kind of shows how many photons you collect from the sky. The third column is root of n star. That is the error in measuring the light from the star. or uncertainty, which is just the root of this number. And the fourth one is the root of the number of photons you collect from the sky. And then you create a quantity called signal to noise ratio, where the signal is the number of photons from your star, and the noise is the total uncertainty in your measurement coming from these two uncertainties or those two noise sources. So if I take a ratio of the total signal versus the total uncertainty in your measurement, if this number is larger than 1, you will be able to see the star. The uncertainty is less than the signal, you will be able to see the star. If the uncertainty is larger than your signal, that the denominator is larger than the numerator, you will not be able to see the star because your noise is larger than your signal. So let us see this situation. I showed you, I mentioned you an illustration where the star is only emitting 1 photons, while the sky is emitting 100 photons. So root of 1 is 1, that is uncertainty in this measurement. Root of 100 is 10. So when you try to subtract the sky, the signal is only 1. The noise is mostly dominated by the sky, which is 10. So the noise is 10 times larger than the signal, and therefore you don't know whether there is a star or not. Now, if you make a telescope which is, let us say, 100 times larger, it can collect 100 times more photons than this one. What happens is the light from your star becomes 100 times. Light from your sky nearby is also gone up by a factor of 100. So instead of 100 photons, you're taking now 10,000 photons from the sky. But the uncertainty in measurement of this is 10. Uncertainty is measuring this is 100. So if I write signal to noise ratio, 100 over the total uncertainty, which is mostly 100. So 100 over 100, it is 1. So you can see that the signal to noise ratio, instead of become 1 over 10, has become 1 because you have made a bigger telescope and collected more light. Let's go on doing it. Make your telescope even 100 times larger. So if the telescope is 100 times larger, you are collecting 100 more times from the star, 100 more times photons from the sky also. So now you are collecting 1,000,000 photons from the sky, but only 10,000 photons from the star. But the uncertainty is in 10,000 is 100, and the uncertainty is measuring this light from the sky is 1,000. So 10,000 over the total noise, which is more like 1,000, 10,000 over 1,000 is 10. Now your signal is 10 times stronger than the uncertainty, and therefore you are going to see a star. So in the same direction of the sky, if you make a very large telescope and point there, in a way that you get 10,000 photons from the star, you may get 1,000,000 photons from the sky nearby. But when you subtract the sky, the noise is only 1,000, and therefore that is 10 times weaker than the signal, which is the extra light coming from the star, and therefore you know there is a star there and you can measure its signal. That is why astronomers make bigger and bigger telescopes, because you collect more light, your measurement error as a fractional error goes down, and therefore you can see fainter and fainter objects, even if the surrounding light from the sky is much brighter. You can see objects which are much fainter than the sky. In this case, in this illustration, I showed you that even if the star is 100 times fainter than the sky, you can still detect light from it, provided you collect enough number of photons with a very large telescope. And that is the reason why astronomers make very large telescopes. Now, here is an illustration of a photograph on the top of a mountain called Mauna Kea. It's an extinct volcano in one of the Hawaiian islands in the middle of the Pacific Ocean. And this mountain is 4,200 meters above the sea level. And you can see there is a large number of very large telescopes on this mountain. I mentioned the Keck telescope in the beginning. So these are 2 Keck telescopes on the top of the mountain. This is an 8-meter telescope set up by the Japanese called the Subaru telescope. This is another 8-meter telescope called the Gemini telescope, and so on and so forth. So very large telescopes set up on the top of this mountain called Mauna Kea in Hawaii. And this is just a zoom up view of the Keck telescope. There are, as I said, there are two of them. The mirror, you can see the main mirror of the telescope is 10 meters in diameter. And there are two of them. So you can see this is a very large structure. You can see this height here at the bottom of the two observatories is like 1 or 2 stories high. And this enormous structure is set up on top of this mountain, which is almost half the height of Mount Everest. So it's an enormous feat to set up these facilities on top of these mountains and carry out astronomical observations from there. And these happen to be the largest optical telescope which are currently existing. But astronomers are building the next generation large telescopes over the next decade or so. Before that, this is a photo which shows 4 8-meter class telescope on a top of a mountain in the Chilean Andes. These are Andes mountains on the west coast of Chile. And in one of those on top of one of those mountains, the Europeans have set up 4 very large 8-meter diameter telescopes. These are called very large telescopes. And then astronomers are building even larger telescopes now. This one is called the Giant Magellan Telescope. It has a net diameter of 24.5 meters. Nobody can make a single mirror of 25 meters or diameter, etc. So the primary mirror of the telescope is made from 7 8-meter class, 8-meter diameter mirrors. So each of these mirrors is 8 meters in diameter. And then you use 7 of them, put them together and align them precisely so that it works like a single surface of about 24.5 meters in diameter. And it's called the Giant Magellan Telescope. This is going to come up in Chile. This is called the European Extremely Large Telescope. It has a diameter of 39 meters. You can see the this is only an image, it's not constructed yet. So the primary mirror of the telescope is 39 meters in diameter. And again, it is not made of a single piece of glass. It is made of about 1,000 individual hexagonal shaped segments. You cannot see the hexagon here except for the edges. 1,000 hexagonal pieces arranged together to form a single surface in a precise fashion so that it becomes a single mirror. And this is again going to come up in Chile. India is participating in one of these facilities called the 30-meter telescope. It is going to come up either in Hawaii or on an island off the coast of mainland Spain called the Tenerife Islands. And again, this is an illustration of how the telescope would look once constructed. This particular image is on a Hawaiian site, and its diameter is 30 meters in diameter, 30 meters in size. And India, along with institutions in the US, China, Japan, and Canada, are part of the consortium which is building this facility. This consortium in India is led by 3 institutes, ARIES in Nainital, IUCAA in Bangalore, and IUCAA in Pune. And these 3 institutes have set up what is called the India TMT Coordination Center, or ITCC, in the IAA website. And this program in India is funded by the Department of Science and Technology and Department of Atomic Energy jointly under the Mega Facilities for Basic Sciences scheme. And it's roughly a 50-50 partnership between the 2 departments of Atomic Energy and Department of Science and Technology. And there are many other institutes in India, in universities and ISAs and IITs, etc., are all participating in India's contribution for building this telescope. So let us, here is an illustration of what the telescope would look like. This is the primary mirror of the telescope, 30 meters in diameter. The light comes from the top, falls on the primary mirror, converges, falls onto the secondary mirror, again converges and comes back to the tertiary mirror here in the middle. And the tertiary mirror then feed it into one of those instruments on the side of the telescope, which will analyze the light and try to tell us what kind of phenomena are going on in the particular object being observed. Now, the construction of this telescope itself is shared by all the partners. You can see different parts of this observatory are being built in different countries, at institutions and industries in different countries. In India, in this corner, we are making a number of parts which are related to the primary mirror of the telescope and its subsystems, along with various other hardware, software, etc. So the main contribution from India is the following. So if I take, you can see this primary mirror telescope. It is made by about 500 individual hexagonal shaped pieces of glass, about 1.4 meters from corner to corner, joined together to form a single surface. So there are about 500 individual hexagonal segments in here. And each of these segments have to be supported in a way that they form a single mirror surface. So in India, if I take one of these segments, you can see at the top, what is shown is one of the hexagonal segments. Some of those segments, less than about 80, less than about 100, maybe from 80 to 100 of those segments, out of the 500 segments will be built in India. We have set up a large optics fabrication facility in Bangalore, where about 100 of these segments will be manufactured in India. Then these segments, when they are placed together, they should form a single surface. And any tiny displacement between the segments have to be measured. And when I say tiny to the level of nanometers, 20 nanometers, 30 nanometers, etc. And those of you who do not understand nanometers, if I take a millimeter, which is a very tiny size, divide it by 1,000, you get a micrometer, and divide it further by 1,000, you get a nanometer. So a millimeter divided by 1,000,000 times is a nanometer. So the relative positions of these individual 500 segments have to be controlled and aligned together to 20 to 30 nanometers in real time, in continuously. The shape should not change. So there are these sensors which are attached to each of these segments. There are 12 sensors attached to each of those segments, which will measure any tiny movement of these segments. And those sensors are all being built in India. Those sensors are which will tell you if the segments are moving relative to each other, and those segments are all being built in India. The actuators which correct the positions of the segments when they move relative to each other, they are also being built in India. This entire support structure, which controls the position of the segments and make sure they remain aligned together, they are also being built in India. So India is making very crucial contribution to the building of this telescope. Now, why do we make this telescope? What are we going to gain? Now, what I'm shown here is an image taken by the Hubble Space Telescope from space, and it's taken a very deep image of a part of the sky. If I zoom into one of those galaxies, which are shown, there are millions of galaxies in this image. If you zoom into one of those galaxies, you will see a picture like this. So this is what a galaxy would look when looked through Hubble, which is in space, outer space, and looking at this area of the sky. So this is a galaxy as can be seen by Hubble. But if I look at the same galaxy with the 30-meter telescope, you can see how fine details you are going to see compared to science. So here is what the Hubble telescope is currently able to see, but here is what the same galaxy may look like when looked through the TMT. So you can see the fine details you can see in that galaxy, the dust lines, the places where the stars are forming, the center of the galaxy, maybe there's a black hole there, and the arms of the galaxy, and so on and so forth. Almost all that is lost even by looking at that galaxy from Hubble on space. So that is the advantage of making a large telescope. You see extremely fine details of extremely faint objects. And one of the things which the TMT would attempt to do is to look for biosignatures, the presence of life in Earth-like stars around Earth-like planets around Sun-like stars. At the moment, with an 8-meter class Gemini telescope, among the largest existing telescope, around Sun-like stars, you can detect very heavy planets like Jupiter-sized planets, or 8 times Jupiter, few times Jupiter-sized planets. You cannot detect Earth-sized planets. So with TMT, we would be able to detect planets which are Earth-like, much lighter than the Jupiter, much more, Jupiter is much more heavier than Earth. So Earth-like planets, and not only detect them, we will also able to study whether the atmosphere of those planets contain biomarkers. If life exists in those planets, like the life which exists on Earth, similar life which exists on those planets, they emit certain kind of radiation, and they emit the certain kind of materials like methane, etc. And you can look for the presence of those biomarkers in Earth-like planets around Sun-like stars. That would be a major discovery if we can make that using the 30-meter telescope. So this is my last slide. I talked to you about 30-meter telescope, which is going to come up, but that is just one of the large facilities which are going to come up over the next decade or so. This is just a collage which shows many other observatories which are under construction or becoming operational over the next 10 years or so, for both from ground and space. So all in all, it's the golden age for astronomy, for discoveries to be made, new understandings of how this universe work and behave. And it's the right time to become an astronomer, because you would be trying to answer some of the most fundamental questions you can ask, like how and when did the universe come into existence? How did these galaxies take birth and evolve into what we see today? Those spiral galaxies, those elliptical galaxies, how did they originate and how did they evolve into what we see as them today? What is the large-scale structure of this universe? Is the universe made of continuous material, or is it made of, how does these galaxies arrange themselves to form the fiber structure of the universe? Is there stuff we can't see, like dark matter, dark energy? And if so, how much of these are existing? What are they made of? Is there life anywhere else in this universe? What are black holes? How are these black holes deciding the life and evolution of galaxies and other physical structures in this universe? You can ask these fantastic questions, and then this telescope like TMT would be able to give you, if not full answers, but at least shine more light into the answers of these questions. Of course, these facilities are all going to generate enormous amount of data, and you need people who can understand data, do data mining, do deep learning, machine learning, and then try to understand what the data these telescopes are going to produce, are trying to tell us. And that is going to be fantastic. And I'm sure over the next decade, 2 decades, enormous discoveries are going to be made by these facilities. And it is going to be really exciting times. Thank you very much.
Thank you, Professor Ramprakash. Amazing talk, and everybody's kind of appreciating it online. If you could see the chats, there are so many chats appreciating the amount of data given, which can be understood by everyone, and the importance of this is known. If you permit, we have a small 2-minute video about the TMT itself. So we'll just play it for everyone to have a more involved look at the TMT.
Sure. Should I stop sharing?
Yes, please. Thanks.
Okay.
We're playing a 2-minute video, and then we'll come back to you.
Okay, no problem.
One question, I think.
Yeah, I'm sorry I took longer than expected, but
Thank you, Professor Ram Prakash. We have one question from audience. So this is asked by Shobhna Kulkarni. The question is, why are 3 different telescopes being built? If there is a 39-meter telescope coming up, then what is the motivation of building others of 24-meter and 30-meter? Why not together build one biggest possible telescope? So can you please answer?
yes, this is very interesting question and very good. Now, what happens is nobody has built a telescope of 25-meter size or more in the past. So when you build a new telescope, it is not clear that what is the right technology, what approaches are going to be successful, and what is going to bring the best quality data from astronomy when you look at it. So different groups are trying to build large telescope, the next generation large telescope, using different technologies and different know-hows. Nobody knows which of them is going to really succeed and become the best. All of us expect them to succeed, but they will succeed in different ways and different levels. That is one reason. So it's not that you try to make one and it will just succeed. You may or may not have the same level of success in each of those cases, or you might take longer to make a particular telescope or particular technology successful compared to the other one. So different groups are trying to do different things at the same time. The second answer is just one telescope is not sufficient to study the whole sky, because there's enormous amount of the wealth of information out there which you want to look at and understand is unlimited. So if you have one telescope and you have, let us say, 365 nights and only 10 hours per light, that is the only time, that is the time which you can collect light from the sky for with one telescope. But the amount of information you want to study and understand is unlimited. So even if there are 10 30-meter class telescope, there are still more things out there which you want to study. So if you look at the previous generation of telescope, like the 8 or 10-meter class telescope, they started with one telescope in the beginning, then you added more, and then there is so much demand for conducting studies with these facilities that you build more. And similarly, as you make 30-meter class telescopes or 25-meter class telescope, there is always demand from astronomers to carry out studies which utilizes these facilities to its best possible extent. And typically what happens is, if for a given night of observing time available on a telescope, there is typically 6 to 10 times more demand than you can accommodate. So if you have a 10-meter class telescope today, and you say, okay, I want to use one of those telescopes to observe, there's 10 times more demand than what can be accommodated. So your chances of succeeding to get a night of observing with a 10-meter class telescope is very, very small. There's so many people out there competing against you to use that telescope. And so you may or may not get. And similarly will be the case of 30-meter class telescope or 25-meter class telescope, where the competition would be even bigger. And therefore we need multiple telescopes to study the sky. And then the next reason is, if you put a telescope in the northern hemisphere of the Earth, you can see a certain part of the sky. You cannot see most of the southern skies from the northern location. So you need a telescope in the northern hemisphere, and you need a telescope in the southern hemisphere to cover the whole sky. So at least you need 2 telescopes, one in the north and one in the south. So this is another reason you need multiple telescopes. And finally, the other question was, why don't everyone put their resources together and make a larger telescope? Let us make, say, a 100-meter diameter telescope. That is fantastic, and we would like to do that. In fact, when people started thinking about making 25 or 30-meter class telescopes, they originally started worrying, can we make a 100-meter telescope? And then people did some feasibility studies, analysis, etc., and then said, look, even in the next 20 years, we will not have the right technology to make a 100-meter class telescope. The technology does not exist today. Even for the 25 or 30-meter class telescope, most of the technologies do not exist. We need to invent those technologies, mature those technologies, and then only you can make even a 25 or 30-meter class telescope. And making straight away a 100-meter class telescope is out of question. So you learned a lot of things by making 8 or 10-meter class telescopes. Those learnings have to be advanced, and new technologies to be developed to make 30-meter class telescopes or 25-meter class telescopes. Eventually, when we perfect those telescopes, over time, we would have the right technology, maybe after 50 years, to make a larger telescope of 100 meters in diameter. And then we will definitely make those 100-meter class telescopes, maybe after 50 years from now, or maybe 100 years from now. But that is our goal.
We're looking forward to that. And I think the students here are inspired enough that they may join the subject and contribute to these future aspirations of astronomers. So I think that will come to the end of this talk. Of course, I have to introduce you as the head of the instrumentation lab, which creates very cutting-edge technology for astronomy observations or observatories. And you'll be happy to know that next lineup, we have a visit to the IUCAA Giravli Observatory. You have a great role in bringing that up and keeping it running and adding advanced technology to it. So that's what we are going into now. Thank you for being here, Professor. And to all the viewers, I will ask you that please stay with us. We have a lot of other amazing and interactive programs coming up even after and stay energized with such great speakers in the morning session. I'm sure you're convinced that the afternoon sessions will also be very interesting. So stay with us. Now we go into the walkthrough, virtual walkthrough. Although we can't go to the place called Giravli, which is about 80 kilometers away from Pune, we are going into the virtual walkthrough. So enjoy that, and After that, we will have some filler videos until the 2 o'clock session, which is the live question and answer session with scientists at IUCAA. So enjoy this, and we'll see you back in a little bit.
Hello friends, my name is Bhushan Joshi. I'm an electronics engineer working in IUCAA Instrumentation Lab. Today we are at IUCAA Giravali Observatory, which is 80 km from Pune city off Pune-Nashik road at the hill of Giravali, which is at the altitude of 1000 meters from mean sea level. So let's get started, let's move in. The telescope was manufactured by Telescope Technology Limited and handed over to IUCAA after installation and commissioning on February 14, 2006. The telescope was formally inaugurated by Professor Yashpal and dedicated to astronomy community on May 13, 2006. After a phase of performance and science verification programs, the observatory is opened for regular observation in November 2006. Behind me is the main telescope building and telescope dome. Let's have a brief introduction about IUCAA Giravali Observatory. In addition to catering to the needs of astronomers, this observatory is unique in setting aside a certain amount of time for training as well as for Indian universities. The architecture of the observatory premises resembles with the architecture of IUCAA. Now we are standing in the lobby of the telescope building. The actual telescope is on the second floor, to which we have access to the staircase. On my right, there is a control room. On my left, there is a coating plant, PLC and power distribution. Let's start with the control room first. Observatory is not only about the optics. It involves many other branches of engineering like mechanical, software and electronics. Control room is a brain of the observatory, from where operator and observer can control the telescope and instruments on it. Operators can command other computers on the telescope through telescope control system. At the same time, they can take a feedback from different sensors from the telescope. The communication from telescope control system to the computers on the telescope happens over copper wires and optical fibers led all through the control room to the telescope structure. Let's have a walkthrough from the control room towards coating plant. We are standing in a control room, and you can see there are plenty of computers around me. So let's see what it is. Here you can see OCC, the main computer. It's called Observatory Control Computer. From here you can give target coordinates, and according to that, telescope moves. On the left hand screen you can see feedbacks from different sensors. This is instrument control computer. From here, observer can control its instrument. And on left hand side, it's a data processing computer where you can post-process the data. Behind here, there is a set of dedicated computers which controls a telescope, dome, and many other things. The important thing in any observatory is the location and the time. We synchronize our location and time using a GPS. So on the roof we have antenna which is synchronized with the satellites, which updates the location and the time information to this computer, which shares this information with every other computer in this room. So in this room, we can see over here, there is a PLC rack, a power distribution box, This is a chiller plant. This is an oil pump. And the most important thing is a mirror coating plant. So let's take information about each component one by one. Few parts of the telescope need continuous lubrication. Also, isolating telescope from vibrations. The complete telescope structure floats on a very thin layer of oil, which has to be pumped continuously on the second floor. This oil pump takes care of filtering and pumping that oil on the second floor of the telescope structure. In this whole process, oil gets heated to a very large temperature. To cool it down to the normal temperature, we use this chiller. Few actuators on the telescope work on pressurized air. To generate it, we can see here a couple of compressors are installed in this room. To operate telescope flawlessly, each component has to perform its job perfectly. PLCs take care of complex algorithms and checks of each and every system on the telescope. Turning on the telescope is not as easy as turning on a single switch. It involves many complex loops, algorithms and protocols which are handled by this PLC rack. PLC stands for Programmable Logic Controller. To operate observatory, we need a lot of electrical power. Power coming from grid, generators and UPS is distributed through this power distribution box. Just like any other reflecting telescope, IGO telescope's mirror also has aluminum coating, which degrades due to oxidation and dust formation. When this coating degrades, we have to bring down the mirror from telescope to this coating plant using sealing cranes. This is complex operation and required a week to complete overall process of taking mirror from the telescope, recoating it and fixing it back on the telescope. As we have seen a mirror coating plant, let me show you one more interesting thing. Let's go inside telescope pier. So this is a main telescope pier supporting the telescope, and this is a telescope building wall. There is a huge gap between both. Why it is so? It's just to avoid any vibration coming from telescope building to the telescope support. We are just standing below the telescope floor. Here you can see a bunch of wires. They are going from control room towards telescope floor. Here there is a special arrangement made to prevent wires from entangling. So finally we are on the telescope floor. Behind me you can see IUCAA 2-meter telescope, which is of Schmidt-Cassegrain type. Between black and blue surface you can see a primary mirror which has a diameter of 2 meters, focal length of 6 meters and thickness of almost 1 foot, and the weight is 1 ton. On top you can see a secondary mirror which has a diameter of 0.6 meter and focal length of 6 meters. The mount of this telescope is called alt-azimuth mount, which has two motions. So one is azimuth motion, which is parallel to the ground, the telescope floor, and other one is altitude, which is perpendicular to the ground. So we have 5 ports available on this telescope. One is main port and 4 side ports. The field of view of main port is 21 arc minutes, which is slightly lesser than a full moon. When we tilt this telescope to see objects near the horizon, the primary mirror deforms due to its own weight. This minor deformation in the primary mirror resulted in a huge distortion in the image. To correct it, we have to push the mirror from the opposite side. The system used in this telescope to correct that distortion is called active mirror support system. This telescope does not have provision to connect an eyepiece. Instead of that, on the main port, we use instrument and charge coupled devices to grab the data. Those CCDs are kept at very low temperature. The temperature is almost minus 100 degrees Celsius. This telescope does not have any port where you can put eyepiece and see by your own eye. Instead of that, we use CCD cameras. The CCD cameras used on the instrument are spatial cameras which has lower noises and high resolutions. The temperature at which the CCDs are kept is almost minus 100 degrees Celsius. We use liquid nitrogen to lower down the temperature of CCDs. When starlight enters in the Earth atmosphere, it is refracted by different layers of it. It is resulted in a scattered images in the ground-based observatories. To nullify this effect, scientists use adaptive optics technology. A new instrument known as RoboEO is currently being installed on this telescope, which will enable adaptive optics and will result in the sharpest possible images.
Observatory has always been one of the major attractions for people. So we have just learned how it operates, and we have seen the beautiful campus, the beautiful building of the telescope. And please stay tuned with us. And before going forward, I would like to let you know that since we are going to stream the next session at 2 o'clock, which is Ask the Scientist session, where we are going to be with Professor Jan Nalikar, Professor Mangaladai Nalikar, Professor Shomak Rai Chaudhary, who will be accompanied with Professor Surud More and Dr. Anuprita More. So before that, right before that, we are going to see one wonderful video. Since we are talking about astronomy and astrophysics, let us see how beautiful these things in the universe are. And before going to that, I would like to request that after the video ends, please refresh your screens or refresh your YouTube videos so that you will be joined to the next live stream of IUCAA, which will be the afternoon session. So thank you very much. Let us see what beautiful objects are there in the universe now. वाओ, दैट वाज रियली अमेजिंग। बहुत ही सुंदर पिक्चर्स हमने देखे। ब्रह्मांड में क्या क्या चीजें हैं, हमारे प्लैनेट से लेकर गैलेक्सीज जिन्हें हम दीर्घिकाएं बोलते हैं, आकाशगंगा है, और बहुत सारी सुंदर सुंदर चीजें, बहुत तारों के बारे में जो बहुत ही सुंदर पिक्चर्स बड़ी बड़ी टेलीस्कोप्स यूज करके लिए गए हैं, वो हमने अभी अभी देखे। और इस सुंदर पिक्चर्स के साथ अब हम आगे बढ़ते हैं हमारे नेक्स्ट सेशन के लिए। मैं आप सभी लोगों से वापस एक बार विनती करना चाहूंगी कि अपनी स्क्रीन एक बार वापस रिफ्रेश कीजिएगा। Please refresh your screen so that we can start with the next session, which is Ask the Scientist. Thank you.